Imagine drifting through the cosmic void, your spacecraft's engines dead, pulled inexorably toward a region of space so dark it devours light itself. Behind you, the stars begin to stretch and distort. Ahead lies nothing but an endless black sphere, growing larger with each passing second. You have just encountered one of the universe's most terrifying phenomena, and there is no escape. The cosmic trap, what lies beyond the point of no return. In the vast theater of space, where galaxies spiral like cosmic whirlpools and stars burn with the fury of a billion hydrogen bombs, there exist regions so extreme that they challenge everything we thought we knew about the nature of reality itself. These are places where space and time become so twisted that the very fabric of the universe breaks down, where the normal rules of physics collapse into mathematical chaos, and where even light, the fastest thing in existence, cannot outrun the crushing grip of gravity. Scientists call them black holes, but this clinical term hardly captures the cosmic horror these objects represent. They are tears in the very structure of spacetime, regions where matter has become so dense that it creates what physicists describe as a singularity, a point where our understanding of the universe simply ends. To accidentally fall into one would be to embark on the ultimate one-way journey, a descent into a realm that exists beyond the boundaries of human comprehension. The story of black holes begins not in the depths of space, but in the equations of a German physicist named Karl Schwarzschild, who in 1916 derived a solution to Einstein's field equations that predicted something so bizarre it seemed like science fiction. Schwarzschild calculated that if enough mass were compressed into a sufficiently small radius, it would create a boundary in space from which nothing could ever return. He called this the Schwarzschild radius, though today we know it by a more ominous name, the event horizon. The mathematics behind this cosmic trap are as elegant as they are terrifying. The Schwarzschild radius follows a deceptively simple formula, Rs equals 2gm/c superscript 2, where g represents Newton's gravitational constant, m is the mass of the object, and c is the speed of light. This equation reveals a chilling truth about the universe. Any object, regardless of its composition, will become a black hole if compressed beyond this critical boundary. Our sun, if somehow crushed into a sphere just 3 kilometers across, would instantly transform into a gravitational monster from which not even light could escape. But what makes the event horizon truly terrifying is not just its role as a cosmic prison, but its nature as a point of no return that exists in a state of perfect camouflage. Unlike the dramatic depictions in science fiction films, real black holes appear as regions of absolute darkness against the star-filled cosmos. They reveal themselves only through their gravitational effects on nearby matter, pulling gas and dust into superheated spiral dances that emit X-rays and gamma radiation before vanishing forever beyond the event horizon. The term event horizon itself carries profound philosophical implications. An event, in physics, is something that can be observed and measured. The horizon represents the limit of what we can see. Combined, they describe a boundary beyond which no events can ever be witnessed by the outside universe. It is a cosmic curtain that forever hides whatever lies within, making black holes perhaps the most perfect keeping of secrets in the entire cosmos. Recent discoveries have revealed that these cosmic monsters come in a staggering variety of sizes, each presenting its own unique form of destruction. The smallest stellar mass black holes, born from the catastrophic collapse of giant stars, contain between 5 and 50 times the mass of our sun compressed into regions smaller than major cities. At the other extreme lurk the supermassive black holes that inhabit the centers of galaxies, containing millions or even billions of solar masses within boundaries that could engulf entire solar systems. The Event Horizon Telescope's historic 2019 image of the black hole at the center of the galaxy M87 provided humanity's first direct glimpse of one of these cosmic monsters. The photograph revealed a ring of glowing matter surrounding a dark central region 6.5 billion times more massive than our sun, with an event horizon spanning 19.5 billion kilometers, so large that Neptune's entire orbit around the sun could fit comfortably inside it. This was not merely a scientific triumph. It was visual confirmation that the universe contains objects so extreme they border on the incomprehensible. Yet even as we celebrate these observational victories, the fundamental question remains, what would actually happen to a human being who crossed this ultimate boundary? The answer, according to our best scientific understanding, depends on factors that read like a cosmic game of Russian roulette. The mass of the black hole, its rate of rotation, and even the presence of nearby matter all influence the precise nature of your doom. Some theoretical physicists argue that crossing the event horizon might feel surprisingly normal, at least initially. According to Einstein's equivalence principle, free fall in a gravitational field is indistinguishable from floating in empty space. This suggests that, for the brief moments after crossing the point of no return, you might not even realize your fate has been sealed. You would continue falling inward, watching the universe you left behind appear to accelerate into fast-forward as relativistic effects compress the remaining history of the cosmos into the final seconds of your existence. But other theories paint a far more violent picture. The firewall hypothesis, proposed by physicists studying the intersection of quantum mechanics and gravity, suggests that the event horizon might be surrounded by a wall of high-energy particles that would incinerate any approaching object instantly. This theoretical firewall would make the event horizon not a gentle boundary but a cosmic death ray operating at the very limits of physical possibility. Perhaps most unsettling of all is the realization that, from the perspective of outside observers, your fall into a black hole would appear to last forever. Due to the extreme time dilation effects near the event horizon, anyone watching your descent would see you gradually slow down, your image becoming increasingly redshifted until you appeared to freeze at the boundary itself, fading slowly into invisibility. To them, you would never actually cross the event horizon. You would remain suspended there for all eternity, a ghostly reminder of the journey from which no traveler returns. This creates one of the most profound paradoxes in modern physics. From your perspective, you cross the event horizon and experience whatever lies beyond in a finite amount of time. But from the universe's perspective, you never actually make it inside. Both views are equally valid according to general relativity, yet they describe completely contradictory realities. It is as if the universe itself cannot decide whether you have been captured by the black hole or forever suspended at its edge. The question of what lies beyond the event horizon has tormented physicists for decades, spawning theories that venture far beyond the boundaries of conventional science. Some propose that black holes might be cosmic tunnels, wormholes connecting distant regions of space and time. Others suggest they could be gateways to parallel universes or even cosmic recycling centers that somehow preserve and redistribute the information of everything they consume. What remains certain is that accidentally falling into a black hole would represent humanity's most extreme scientific experiment, a journey to the very limits of space and time that would test our understanding of reality itself. The cosmic trap awaits, patient and invisible, scattered throughout the universe like hidden landmines in the fabric of space-time. But the terrifying beauty of this scenario lies not just in its finality, but in its absolute mystery. What secrets do these cosmic monsters guard beyond their event horizons? What happens to matter, energy, and information when they cross the ultimate boundary? And perhaps most haunting of all, in a universe filled with billions of black holes, how many cosmic travelers have already made this journey into the unknown, their final discoveries forever hidden behind the veil of the event horizon? The answers to these questions may determine not just the fate of any unfortunate space traveler, but our understanding of the universe itself. The monsters lurking in space. Not all black holes are created equal. Yet not all cosmic monsters are created equal, and understanding the differences between these gravitational behemoths could mean the difference between instant obliteration and a surprisingly gentle journey to oblivion. Scattered throughout the universe like invisible predators of vastly different sizes and temperaments, black holes exist in distinct categories, each offering its own unique form of destruction. Some tear you apart before you even glimpse their event horizons, while others welcome you across their boundaries with deceptive hospitality, allowing you precious hours to contemplate your fate before delivering the final blow. The most violent and immediately deadly are the stellar mass black holes, cosmic killers born in the universe's most cataclysmic events. These monsters emerge when stars at least 20 to 25 times more massive than our Sun reach the end of their nuclear lives and collapse in supernova explosions so powerful they briefly outshine entire galaxies. In less than a second, the star's core implodes under its own gravity, crushing matter to densities that defy human comprehension. A teaspoon of this material would weigh as much as Mount Everest. The resulting black holes typically contain between 5 and 50 solar masses compressed into regions smaller than major metropolitan areas. Cygnus X1, one of the first confirmed black holes and a cosmic monster that has captured the imagination of scientists for decades, contains approximately 21 times the mass of our Sun squeezed into a sphere just 124 kilometers across. This seemingly modest size conceals a gravitational field so intense that it creates what can only be described as a death zone extending far beyond the event horizon itself. What makes stellar mass black holes particularly terrifying is their compact nature, which generates extreme tidal forces, the difference in gravitational pull between your head and your feet. The mathematical relationship governing this cosmic torture follows a deceptively simple formula. Tidal acceleration equals 2 g/r superscript 3, where L represents your body length and r is your distance from the black hole's center. This equation reveals a chilling truth. Smaller black holes create exponentially stronger tidal gradients that would rip you apart long before you could cross their event horizons. For a typical 8 solar mass stellar black hole, these lethal tidal forces manifest at distances of approximately 700 kilometers from the event horizon, meaning your body would begin stretching uncomfortably at roughly twice the altitude of the International Space Station. The process starts as a gentle pull, similar to the sensation of someone gently stretching your spine, but quickly escalates into agony as the differential forces exceed your body's structural limits. Military trauma research suggests that differential forces of approximately 2,000 pounds, equivalent to a small car pressing down on your chest while another pulls your legs in the opposite direction, represent the threshold beyond which human tissue begins to fail catastrophically. For stellar mass black holes, you would experience these lethal forces while still hundreds of kilometers away from the point of no return, making your death not just inevitable but gruesome in its mechanical precision. The spaghettification process unfolds with horrifying inevitability. Your feet, being closer to the black hole, experience stronger gravitational acceleration than your head, creating a stretching effect that begins gently but accelerates exponentially. Computer simulations show that the stretching starts slowly, perhaps a few millimeters per second initially, but the tidal forces grow stronger as you fall closer. Within seconds, the differential becomes unbearable. Your spine elongates beyond its natural limits, organs shift and compress, and blood flow becomes impossible as your circulatory system stretches beyond function. The final moments involve your body rupturing at its weakest structural point, typically just above the hips where your torso meets your pelvis. Death comes not from the black hole itself, but from massive internal trauma as your organs and blood vessels fail under impossible stresses. Your separated pieces continue falling and stretching until they are reduced to individual atoms, creating the macabre, spaghetti strands that give this phenomenon its deceptively playful name. At the opposite end of the cosmic spectrum lurk the supermassive black holes, gentle giants that inhabit the centers of most large galaxies like slumbering dragons jealously guarding their territories. These monsters contain millions to billions of solar masses, with event horizons so vast they could encompass entire solar systems. The supermassive black hole at the center of our own Milky Way galaxy, known as Sagittarius A*, pronounced Sagittarius A*, contains 4.3 million times the mass of our Sun within an event horizon stretching 12 million kilometers across. What makes these cosmic giants paradoxically more hospitable than their smaller cousins is their sheer size. The mathematical relationship governing tidal forces means that larger black holes create gentler gravitational gradients. At the event horizon of Sagittarius A*, the tidal forces amount to just a 0.02% difference between your head and feet, far below the threshold of human detection. You could cross this boundary without even realizing you had entered the point of no return. The Event Horizon Telescope's groundbreaking 2019 image of M87's central black hole revealed an even more massive monster, a supermassive black hole containing 6.5 billion solar masses with an event horizon spanning 19.5 billion kilometers. To put this in perspective, this cosmic giant's event horizon is so large that Neptune's entire 5.9 billion kilometer orbit around our Sun could fit comfortably inside it with room to spare. Yet paradoxically, crossing this boundary would feel gentler than riding in a smooth elevator. NASA's 2024 supercomputer simulations of falling into a Milky Way equivalent supermassive black hole calculated a survival time of approximately 12.8 seconds from event horizon to singularity, during which you would travel nearly 130,000 kilometers through increasingly warped spacetime. However, this represents the minimum survival time under direct radial infall. More sophisticated trajectory analysis suggests that optimal approach angles and initial conditions could extend your survival to several hours inside the event horizon. Precious time to witness phenomena that no human has ever observed. Recent theoretical calculations indicate that black holes exceeding 1,000 solar masses allow humans to cross their event horizons alive and conscious, while those larger than 100,000 solar masses make the crossing so gentle that tidal effects become negligible. The most massive known black holes, such as TON 618 with its staggering 66 billion solar masses, could theoretically provide days or even weeks of survival time inside their event horizons, as their boundaries encompass regions with average matter densities lower than water. Between these extremes exists a mysterious middle ground that has long puzzled astronomers: intermediate mass black holes containing roughly 100 to 100,000 solar masses. These objects represent the missing link in black hole demographics, bridging the gap between stellar mass and supermassive varieties. Until recently, they existed more in theory than observation, leading some scientists to wonder if nature somehow avoided creating black holes in this mass range. The breakthrough came through gravitational wave astronomy. In May 2019, the LIGO and Virgo detectors recorded GW 190521, the merger of two black holes with masses around 85 and 66 solar masses, creating a final black hole of approximately 142 solar masses. This detection provided the first direct evidence for intermediate mass black holes and opened a new window into understanding how these cosmic monsters form and evolve. Even more dramatic was the November 2023 detection of GW 231123, which shattered previous records with the merger of two black holes containing roughly 100 and 140 solar masses, producing a final monster weighing approximately 225 solar masses. Both original black holes were spinning at near maximum rates, a discovery that challenges current stellar evolution models, which predict that such massive objects shouldn't exist through conventional star formation processes. From a survival perspective, intermediate mass black holes occupy a dangerous middle ground. They are large enough that you might survive the initial approach to their event horizons, but small enough that tidal forces would likely kill you within minutes or hours of crossing the boundary. A 1,000 solar mass black hole would have an event horizon about 3,000 kilometers in radius, large enough for a gentle crossing but compact enough for lethal tidal forces to develop quickly once inside. Perhaps most mysterious of all are the primordial black holes, theoretical objects that may have formed in the universe's first second through density fluctuations in the primordial plasma. Unlike stellar mass black holes, which require the collapse of massive stars, primordial black holes could theoretically exist across an enormous range of masses, from microscopic objects smaller than atomic nuclei to giants rivaling supermassive black holes. If primordial black holes exist in large numbers, they could solve several cosmic mysteries simultaneously. Small primordial black holes might constitute the dark matter that makes up 85% of the universe's mass but remains invisible to our telescopes. Larger primordial black holes could serve as the seeds from which supermassive black holes grew in the universe's youth, explaining how such massive objects could exist just a few 100 million years after the Big Bang. NASA's upcoming Nancy Grace Roman Space Telescope will search for these exotic objects through gravitational microlensing, the temporary brightening of background stars as primordial black holes pass in front of them. If successful, these observations would reveal an entirely new population of cosmic monsters lurking invisibly throughout the universe, each presenting its own unique threat to any unfortunate space traveler. The diversity of black holes scattered throughout the cosmos means that your fate, should you accidentally encounter one, depends entirely on cosmic chance. Stumble into a stellar mass black hole, and your journey ends in violent dismemberment before you can even comprehend your situation. Drift toward a supermassive giant, and you might cross the event horizon with time to spare for final contemplations of the universe you're leaving behind. But regardless of which cosmic monster claims you, one truth remains constant. You have entered a realm where the normal rules of physics begin to break down, where space and time become so warped that cause and effect lose their meaning, and where the ultimate secrets of the universe wait beyond a boundary that no information can ever cross. The mathematics of doom. How physics seals your fate. Yet behind these cosmic monsters of varying sizes and temperaments lies something far more terrifying than their gravitational might. The cold, inexorable mathematics that seals your fate the moment you venture too close. These are not mere equations scribbled on a physicist's blackboard, but fundamental laws of the universe that operate with the precision of a cosmic guillotine. Every black hole, regardless of its mass or origin, follows the same mathematical principles that transform ordinary spacetime into an inescapable prison, where the very geometry of reality conspires against any hope of return. The story of this mathematical doom begins in 1915, when Albert Einstein published his theory of general relativity and forever changed humanity's understanding of gravity. Unlike Newton's conception of gravity as a mysterious force pulling objects together across empty space, Einstein revealed gravity to be something far more profound and terrifying: the curvature of spacetime itself. Massive objects don't pull on other objects. Instead, they warp the very fabric of space and time, creating valleys and slopes in the four-dimensional landscape of the universe. Imagine spacetime as a vast rubber sheet stretched taut across the cosmos. Place a bowling ball in the center, and it creates a depression that causes marbles rolled nearby to curve toward it. This analogy, while imperfect, captures the essence of Einstein's revelation. Gravity is geometry, and massive objects reshape the universe around them. But Einstein's equations predicted something even more extreme. If enough mass were concentrated in a small enough region, it would create a pit so deep that nothing, not even light itself, could climb back out. Just 1 year after Einstein published his field equations, German physicist Karl Schwarzschild derived a solution that would haunt physicists for generations. Working on the Russian front during World War I, Schwarzschild calculated what spacetime would look like around a perfectly spherical, non-rotating massive object. His solution revealed a critical radius, now known as the Schwarzschild radius, where the curvature of spacetime becomes so extreme that it forms what mathematicians call a coordinate singularity. The mathematics behind this cosmic boundary are deceptively elegant. The Schwarzschild radius follows the formula Rs equals 2gm/c superscript 2, where g represents Newton's gravitational constant, 6.674 times 10 superscript 1 superscript 1m superscript 3/kgs superscript 2. M is the mass of the object, and c is the speed of light, 299,792,458 meters per second. This simple equation contains within it the blueprint for the universe's most perfect prisons. Any object compressed within its Schwarzschild radius becomes a black hole, creating an event horizon from which escape becomes mathematically impossible. The numbers themselves reveal the terrifying scale of compression required. Our Sun, with its mass of 1.989 times 10 superscript 3 kilograms, would need to be squeezed into a sphere just 2.95 kilometers in radius, smaller than most cities, to become a black hole. Earth, despite its considerable mass of 5.972 times 10 superscript 2 kilograms, would create a black hole with a Schwarzschild radius of merely 8.87 millimeters, smaller than a marble. The entire observable universe, containing approximately 10 superscript 3 kilograms of matter, would fit within a black hole just 13.7 billion light-years in radius, roughly the size of the observable universe itself. But the true horror of Schwarzschild's mathematics becomes apparent when you examine what happens to spacetime near this critical boundary. The metric tensor, the mathematical object that describes the geometry of spacetime, contains terms that grow larger and larger as you approach the Schwarzschild radius. At the event horizon itself, certain components of Einstein's field equations appear to become infinite, suggesting that the curvature of spacetime reaches impossible extremes. Modern physicists understand that these mathematical infinities represent not physical reality but the breakdown of the coordinate system Schwarzschild used. Like trying to describe the surface of Earth using longitude and latitude coordinates at the North Pole, where all meridians converge, Schwarzschild's original coordinates become meaningless at the event horizon. Other coordinate systems, such as those developed by Kruskal and Zacharies, reveal that spacetime remains perfectly smooth at the event horizon, but this mathematical subtlety provides no comfort to anyone crossing this boundary. The mathematics of general relativity reveal why escape from within the event horizon becomes impossible through what physicists call causal structure. In normal spacetime, you can always find paths that lead into the future while moving away from any particular location. Inside a black hole, however, the extreme curvature of spacetime tilts the light cones, mathematical objects that describe which directions you can travel through space and time, so severely that all future-directed paths lead inexorably toward the central singularity. This creates one of the most unsettling aspects of black hole physics. Once inside the event horizon, the radial coordinate becomes time-like rather than space-like. In ordinary space, you can choose to move left or right, forward or backward, up or down. But you cannot choose to move backward in time. Time flows in only one direction. Inside a black hole, falling toward the center becomes as inevitable as aging. No amount of rocket thrust, regardless of its power, can prevent your approach to the singularity, because doing so would require traveling backward in time. The mathematical description of this geometric trap involves the concept of geodesics, the paths that objects follow through curved spacetime when no external forces act upon them. In flat spacetime, geodesics are straight lines. Near massive objects, they curve. But inside a black hole's event horizon, all geodesics converge toward the central singularity within a finite proper time. The mathematics show that you have approximately pi times the Schwarzschild radius divided by the speed of light to live once you cross the event horizon, a death sentence written in the fundamental equations of spacetime itself. Einstein's field equations also reveal why the event horizon acts as a one-way membrane. Light rays emitted radially outward from just inside the event horizon follow geodesics that curve back inward, never escaping to the outside universe. Light rays emitted at an angle fare no better. The extreme curvature of spacetime bends all light paths toward the center. From a mathematical perspective, the event horizon represents what geometers call a null surface, a boundary that light can cross in only one direction. The implications extend beyond simple geometry to the fundamental nature of information itself. If general relativity is correct, then anything falling past the event horizon, including information about its quantum state, becomes causally disconnected from the rest of the universe. The mathematical formalism of general relativity provides no mechanism for information to escape from inside the event horizon, leading to what physicists call the black hole information paradox. This mathematical prison becomes even more confining when you consider the effects of rotation. Most real black hole spin, and the mathematics of rotating black holes, described by the Kerr metric discovered in 1963, reveal even stranger geometric properties. Rotating black holes drag spacetime around with them in a phenomenon called frame dragging, creating regions where it becomes impossible to remain stationary relative to distant stars. The mathematics show that near a rotating black hole, you must orbit in the same direction as the black hole's rotation simply to avoid falling in, like trying to swim upstream in a river flowing faster than you can swim. The mathematical description of tidal forces reveals another layer of doom encoded in the equations. The Riemann curvature tensor, which describes how spacetime curves, contains components that grow without bound as you approach the central singularity. These mathematical terms correspond to physical tidal forces that stretch objects in one direction while compressing them in others. For stellar mass black holes, the tidal acceleration formula A equals 2gm/ are superscript 3 times L, where L is your body length, shows that these forces become lethal long before you reach the event horizon. Perhaps most unsettling of all is what the mathematics reveal about the central singularity itself. As you approach the center of a black hole, both the curvature of spacetime and the tidal forces grow without limit. The metric components of Einstein's field equations diverge to infinity, indicating that our current understanding of physics breaks down completely. At the singularity, density becomes infinite, spacetime curvature becomes infinite, and the very concept of space and time loses all meaning. General relativity predicts that you will reach this singularity in a finite amount of proper time, typically just fractions of a second for stellar mass black holes, or hours for supermassive ones. The mathematics show no mechanism to prevent this encounter with infinite curvature, suggesting that the singularity represents not just the end of your journey, but the end of physics itself. At this point, Einstein's equations cease to provide meaningful predictions, and the mathematical framework that describes the rest of the universe simply stops working. Modern attempts to resolve these mathematical infinities have led to exotic proposals involving quantum gravity, string theory, and loop quantum gravity. Some theories suggest that quantum effects might prevent the formation of true singularities, replacing them with exotic objects like grainy space at the Planck scale or bouncing geometry that could theoretically emerge as a white hole in another region of spacetime. But these remain speculative solutions to mathematical problems that may not reflect physical reality. The mathematics of black holes also encode strange predictions about time itself. As you fall toward the event horizon, outside observers watching your descent would see you slow down due to gravitational time dilation. The mathematical relationship T equals T/square root 1 rs/r shows that your clocks appear to run increasingly slowly as you approach the Schwarzschild radius. At the event horizon itself, this formula predicts that your time appears to stop completely from an external perspective. You would seem to freeze at the boundary forever, gradually fading from view as your light becomes increasingly redshifted. Yet from your own perspective, the mathematics tell a different story. Your proper time continues normally, and you cross the event horizon in finite time, typically around 0.0001 seconds for a solar mass black hole. This creates a mathematical paradox. From outside, you never cross the event horizon, but from your perspective, you do. Both descriptions emerge from the same equations, yet they describe completely contradictory realities. This mathematical schizophrenia reflects a deeper truth about black holes. They exist at the boundary between the physics we understand and the physics we don't. The equations of general relativity, which describe black holes with stunning precision, simultaneously predict their own breakdown at the central singularity. They create perfect mathematical prisons while acknowledging that they cannot describe what lies at the heart of these cosmic jails. The mathematics of doom that govern black holes operate with the cold indifference of natural law, caring nothing for human hopes or fears. They represent the universe's most fundamental statement about the nature of causality. Some boundaries, once crossed, can never be uncrossed. Some journeys, once begun, can never be reversed. And some mathematical truths, once confronted, reveal that the cosmos operates according to laws far stranger and more absolute than human intuition could ever imagine. Two paths to destruction. Your death depends on your target. But mathematics, no matter how elegant or terrifying, remains an abstraction until it encounters the fragile reality of human flesh and bone. The cold equations that govern black holes care nothing for your hopes, fears, or desperate attempts at escape. They simply describe, with ruthless precision, how the universe will dismantle you atom by atom. Yet hidden within these mathematical certainties lies a cruel cosmic lottery. Your method of death depends entirely on which gravitational monster fate delivers you to. Choose poorly, and you face a torture that unfolds over agonizing seconds. Choose wisely, if such a word can apply to falling into a black hole, and you might cross the threshold of oblivion with surprising dignity intact. The first path to destruction, reserved for those unfortunate enough to encounter stellar mass black holes, represents perhaps the most gruesome death imaginable in the known universe. These compact killers, born from the collapsed cores of massive stars, pack tremendous gravitational fields into relatively small spaces, creating what can only be described as cosmic torture chambers that begin their work long before you approach their event horizons. The process begins subtly, almost gently, as you fall from a safe distance toward your doom. At first, the sensation resembles nothing more threatening than the mild stretching you might feel during a morning yoga routine. Your spine elongates slightly, your limbs extend, and you experience what astronauts call the spaghetti effect. Though this clinical term hardly captures the horror that awaits. The mathematics governing this cosmic torture follow the tidal acceleration formula, a differential force equal to 2 gm times your body length, divided by the cube of your distance from the black hole's center. For Cygnus X1, one of the most studied stellar mass black holes containing 21 times our Sun's mass, these forces begin to manifest at approximately 1,000 kilometers from the black hole's center, while the event horizon lies just 62 kilometers away. This means your destruction begins at a distance equivalent to the altitude of some satellites, in the cold vacuum of space where you can still see stars and perhaps convince yourself that escape remains possible. As you continue falling, the differential between the gravitational pull on your feet versus your head grows exponentially stronger. What began as gentle stretching becomes uncomfortable tension, then painful strain, and finally unbearable torment as forces equivalent to being drawn and quartered by invisible horses begin tearing at your body. Military medical research indicates that differential forces exceeding 2,000 pounds, roughly the weight of a small automobile, represent the threshold beyond which human tissue begins catastrophic failure. The stretching process follows a predictable anatomical progression that reads like a coroner's nightmare. Your spine, designed to support your body weight under Earth's gentle 1g acceleration, begins elongating beyond its natural limits as gravitational forces overwhelm the tensile strength of ligaments and cartilage. Intervertebral discs compress on one side while expanding on the other, creating asymmetric pressures that send waves of agony through your nervous system, assuming your nervous system remains intact long enough to register pain. Your circulatory system faces its own impossible challenge as blood vessels stretch beyond their elastic limits. The heart, evolved to pump blood through a roughly 2-meter-tall human body, suddenly finds itself attempting to circulate blood through an increasingly elongated form that may stretch to 3 meters, then 4, then more. Blood pressure gradients that never existed in terrestrial evolution create regions where circulation becomes impossible, starving organs and tissues of oxygen, while others face dangerous hypertension. The crescendo of destruction arrives when your body reaches its ultimate breaking point, typically occurring just above the hips where your torso meets your pelvis, the anatomical weak point where your body's structural integrity finally surrenders to the inexorable mathematics of tidal forces. The rupture happens suddenly, violently, and completely, separating your upper and lower body with the mechanical precision of cosmic forces that recognize no distinction between flesh and any other form of matter. But death in the jaws of a stellar mass black hole offers no peace. Your severed pieces continue their journey toward the event horizon, each fragment subject to the same relentless stretching forces that claimed your intact body. Arms separate from torso, legs from hips, and the process continues down to increasingly smaller scales. Tissues pull apart, cells rupture, and eventually even molecules succumb to the differential forces, reducing what was once a thinking, feeling human being to a stream of individual atoms spiraling toward the event horizon in a grotesque parody of the cosmic recycling process. Computer simulations tracking this macabre journey show that for a typical 8 solar mass black hole, the entire spaghettification process unfolds over approximately 0.8 seconds from the first uncomfortable stretching to complete atomic dissolution. During this brief eternity, you experience forces that no human physiology could possibly survive, creating a death that is both instantaneous on cosmic scales and agonizingly prolonged on human ones. The second path to destruction could hardly be more different. Supermassive black holes, those gentle giants lurking at the centers of galaxies, offer what might generously be called a civilized death, if any demise involving cosmic annihilation can be described as civilized. These monsters, containing millions or billions of times our sun's mass, create event horizons so vast that crossing them feels less like entering a death trap and more like passing through an invisible doorway into another realm entirely. Sagittarius A*, the supermassive black hole residing at our galaxy's heart, creates an event horizon stretching 12 million kilometers across, roughly 17 times the radius of our sun. At this boundary, the tidal forces amount to just 0.02% difference between your head and feet, far below the threshold of human perception. You could cross this cosmic point of no return without feeling so much as a gentle tug, let alone the violent dismemberment that characterizes stellar mass encounters. NASA's sophisticated computer simulations of falling into supermassive black holes reveal a journey markedly different from the violent shredding associated with their smaller cousins. From the moment you cross the event horizon of a Milky Way equivalent black hole to your final encounter with the central singularity, you would survive approximately 12.8 seconds, an eternity compared to the fraction of a second death sentence imposed by stellar mass monsters. During these precious seconds, you would travel nearly 130,000 kilometers through increasingly warped spacetime, experiencing phenomena that no human has ever witnessed. The mathematics show that with optimal trajectory planning, angling your approach to maximize orbital angular momentum rather than falling straight inward, you could theoretically extend your survival time to several hours inside the event horizon. This possibility transforms your final journey from a brief plunge into an extended exploration of physics operating under the most extreme conditions in the universe. The critical mass threshold that determines your fate lies at approximately 1,000 solar masses. Black holes smaller than this limit subject you to lethal tidal forces at their event horizons, while those exceeding this boundary allow you to cross intact. At 100,000 solar masses, the threshold for truly gentle crossings, tidal effects become so mild that you might not realize you've entered the cosmic point of no return until the universe outside begins behaving strangely due to extreme gravitational effects. The most massive known black holes push the boundaries of gentleness to almost absurd extremes. TUN 618, containing an estimated 66 billion solar masses, creates an event horizon so vast that its average density approaches that of water. Crossing this boundary would feel no more dramatic than swimming through a perfectly calm ocean, despite the absolute certainty that you're entering a region from which no information can ever escape to tell the outside universe of your discoveries. Recent theoretical calculations suggest that the largest supermassive black holes could provide weeks or even months of survival time for anyone unfortunate enough to fall into them. During this extended period, you would witness the universe outside experiencing extreme time dilation effects, watching millions of years of cosmic evolution compressed into moments as stellar populations age, galaxies collide, and the cosmos itself undergoes transformations normally requiring geological timescales. The boundary between these two fates, violent dismemberment versus gentle crossing, represents one of the universe's most profound examples of how scale determines destiny. The difference between a 50 solar mass stellar black hole and a 50-million solar mass supermassive monster is not merely quantitative but qualitative, transforming the entire nature of the experience from mechanical torture to what might almost be described as a philosophical meditation on the nature of existence itself. Yet regardless of which path fate selects for you, both lead to the same ultimate destination: the central singularity where space-time curvature becomes infinite and the known laws of physics break down completely. The mathematics that govern both scenarios converge at this point where density, temperature, and gravitational forces reach values that have no meaning within our current understanding of reality. The cosmic lottery that determines your method of destruction operates according to the same random processes that scattered black holes throughout the universe billions of years ago. There is no cosmic justice in this selection, no correlation between the magnitude of your theoretical crime in falling into a black hole and the severity of your punishment. A child who accidentally drifts too close to a stellar mass black hole faces infinitely more suffering than a mass murderer who happens to encounter a supermassive giant. This arbitrary distribution of cosmic justice or injustice reflects a deeper truth about the universe itself. The cosmos operates according to physical laws that recognize no moral distinctions, no gradations of desert or worthiness. The same gravitational equations that govern the gentle rotation of planets around stars also dictate the violent dismemberment of anything foolish enough to venture too close to compact gravitational monsters. In the end, your death depends not on your choices, your preparations, or your worthiness, but on the simple cosmic accident of which type of gravitational monster happened to be waiting in your particular corner of spacetime. The universe offers you two paths to destruction, each following the same fundamental laws but producing experiences as different as gentle sleep and violent awakening. The mathematics care nothing for your preference. When time becomes your enemy, the relativity nightmare. Yet even as you face the binary choice between violent dismemberment and gentle oblivion, the universe reserves its cruelest trick for last: the complete betrayal of time itself. In your final moments, that most fundamental dimension of existence, the steady, reliable progression of seconds, minutes, and hours that has governed every moment of your life becomes your enemy. Time stretches, compresses, and ultimately abandons you entirely, creating a nightmare scenario where past, present, and future lose all meaning. This is Einstein's relativity unleashed in its most extreme form, where the simple act of falling transforms you into a temporal exile, forever severed from the universe you once called home. The horror begins long before you reach the event horizon, manifesting first as a subtle wrongness in the way light behaves around you. As you accelerate toward the black hole under its inexorable gravitational pull, the fundamental relationship between space and time that Einstein revealed in 1905 begins working against you with increasing malevolence. The special theory of relativity, which seems so elegant and abstract in physics textbooks, becomes a lived nightmare as your velocity approaches significant fractions of light speed. Time dilation, that gentle academic concept that once allowed physicists to calculate the slight age differences between earthbound observers and high-speed travelers, transforms into a cosmic torture device operating on scales that dwarf human comprehension. The mathematical relationship governing this temporal nightmare follows the Lorentz factor, gamma equals 1/square root 1 v superscript 2 c superscript 2, where v represents your velocity and c is the speed of light. As your velocity increases, this factor grows larger, meaning time passes increasingly slowly for you relative to the outside universe. But this represents only the first layer of temporal horror. Einstein's general theory of relativity adds gravitational time dilation to the nightmare, creating effects that compound your temporal isolation exponentially. The mathematics follow the relationship T equals T square root 1 rs/r, where rs is the Schwarzschild radius and r is your distance from the black hole's center. As you fall closer to the event horizon, this factor approaches zero, meaning your time slows to a crawl relative to distant observers. The combined effects create a scenario that challenges the very meaning of simultaneous experience. From your perspective, falling toward a stellar mass black hole from a distance of several thousand kilometers might take only minutes of subjective time. Yet for anyone watching your descent from a safe distance, this same journey appears to unfold over hours, days, or even years. The universe literally cannot agree on when events occur, creating multiple valid but contradictory descriptions of reality itself. As you accelerate past 10% of light speed, a velocity easily achieved during gravitational free fall toward a black hole, the outside universe begins exhibiting disturbing behavior. Stars ahead of you shift toward blue due to the relativistic Doppler effect, their light compressed to higher frequencies and intensities. Behind you, the cosmos redshifts dramatically, with familiar stellar patterns fading into deep infrared wavelengths invisible to human eyes. The universe appears to contract in the direction of your motion while expanding perpendicular to it, creating visual distortions that transform the familiar star field into an alien landscape. At 50% of light speed, these effects become overwhelming. The universe ahead compresses into an increasingly narrow cone of brilliant blue-white light, while everything behind you disappears into an expanding zone of darkness punctuated only by the faint red glow of extremely redshifted photons. You begin experiencing what relativists call optical beaming, the tendency for light to concentrate in your direction of motion, creating the illusion that the entire universe is rushing toward you while simultaneously fleeing behind. The approach to 90% of light speed unleashes Einstein's most counterintuitive predictions. The starfield ahead contracts into a brilliant ring of light that appears to encircle your entire field of view, a phenomenon created by photons following curved paths through spacetime, arriving at your position from directions that seem geometrically impossible. This ring grows brighter and more compressed as your velocity increases, eventually containing the redshifted light of the entire observable universe compressed into an increasingly narrow band. Meanwhile, gravitational time dilation adds its own layer of temporal distortion. As you fall closer to the event horizon, the time dilation factor grows exponentially. At a distance of 10 Schwarzschild radii from a solar mass black hole, your clocks run approximately 5% slower than those of distant observers. At 5 radii, the difference increases to 13%. At 2 radii, your time crawls at roughly half the rate of the outside universe. The approach to the event horizon itself triggers effects that border on the incomprehensible. At 1.1 times the Schwarzschild radius, just 10% outside the point of no return, your time dilation factor reaches approximately 3.16, meaning every second you experience corresponds to more than 3 seconds in the outside universe. At 1.01 times the Schwarzschild radius, this factor explodes to over 10, creating a temporal gulf that transforms minutes of your experience into hours of external time. For observers watching your descent, the effects create a scene that resembles a cosmic horror film. They see you slowing down as you approach the event horizon, your movements becoming increasingly lethargic as gravitational time dilation takes hold. Your image becomes redshifted, taking on an increasingly crimson hue as the photons climbing out of the black hole's gravitational well lose energy and stretch to longer wavelengths. Eventually, you appear to freeze at the event horizon itself, your final image fading slowly from view as it redshifts beyond the visible spectrum. From their perspective, you never actually cross the event horizon. Instead, you remain suspended there forever, a ghostly reminder of your journey gradually fading into invisibility over a period that could last thousands or even millions of years, depending on the black hole's mass. To them, you have become a temporal exile, frozen at the boundary between the known universe and the unknowable realm beyond. Your experience tells a radically different story. From your reference frame, you cross the event horizon in finite proper time, typically fractions of a second for stellar mass black holes or several minutes for supermassive ones. The crossing itself feels remarkably unremarkable, particularly for large black holes where tidal forces remain gentle. You pass through what seems like empty space, continuing your inward journey with no dramatic moment marking your transition into the point of no return. But the universe outside begins behaving in increasingly bizarre ways. Due to the extreme time dilation, you observe the external cosmos accelerating into fast-forward motion. Stars that normally evolve over millions of years complete their entire life cycles in moments. Stellar nurseries collapse into newborn stars, which rapidly burn through their nuclear fuel, swell into red giants, and explode as supernovae in accelerated sequences that compress cosmic timescales into human-perceptible intervals. The view behind you, toward the outside universe, becomes dominated by a phenomenon physicists call the Einstein ring. All the light from the cosmos outside the black hole becomes gravitationally lensed into a brilliant circle that appears to contain the compressed image of the entire observable universe. Within this ring, you witness the accelerated evolution of galaxies, the birth and death of countless stars, and potentially even the heat death of the universe itself as cosmic expansion and entropy play out their final act in the span of your remaining lifetime. The mathematics governing these effects reveal why time becomes your ultimate enemy. The proper time tau you experience relates to coordinate time t through the metric tensor of curved spacetime. d tau superscript 2 equals 1 rs/r dt superscript 2 dr superscript 2 slash c superscript 2 1 rs/r r superscript 2 d omega superscript 2 slash c superscript 2. This deceptively complex equation encodes the fundamental truth that space and time become inextricably mixed near black holes, creating effects that violate every intuitive understanding of temporal flow. Inside the event horizon, the situation becomes even more nightmarish. The radial coordinate r becomes time-like, meaning that falling toward the center becomes as inevitable as aging. The mathematics show that all future-directed world lines, all possible paths you could take through spacetime, lead inexorably toward the central singularity. Time itself conspires to ensure your destruction, making escape not just difficult but literally meaningless within the context of causal physics. The gravitational redshift formula Z equals square root 1 rs/r / 1 rs/r. 1 reveals how photons struggle against the black hole's gravitational field, losing energy as they climb out of the gravitational well. For light emitted from near the event horizon, this redshift becomes infinite, meaning outside observers can never receive information about your experiences once you cross the boundary. You become causally disconnected from the rest of the universe, your discoveries and final moments forever hidden behind the event horizon's temporal veil. Perhaps most disturbing of all is the realization that your temporal isolation operates according to immutable physical laws rather than cosmic malice. The universe isn't actively torturing you with time dilation effects. It's simply following the mathematical relationships that govern all spacetime curvature. The same equations that describe the gentle precession of Mercury's orbit also dictate your temporal exile, operating with the indifferent precision of natural law. Modern research into black hole physics has revealed even stranger temporal possibilities. Some theoretical models predict that the interior of black holes might contain closed time-like curves, paths through spacetime that loop back on themselves, potentially allowing causal paradoxes where effects precede their causes. While these remain speculative, they suggest that your final moments might unfold in ways that violate not just intuitive understanding but fundamental assumptions about causality itself. The study of black hole thermodynamics has revealed connections between event horizons and the arrow of time that govern entropy increase throughout the universe. Stephen Hawking's discovery that black holes emit thermal radiation suggests that your fall into the black hole contributes to the universe's total entropy, making your destruction not just a personal tragedy but a cosmic inevitability written into the second law of thermodynamics. Recent developments in holographic theory suggest that your temporal exile might be even more profound than classical general relativity predicts. If the holographic principle is correct, then your entire journey, including your experiences inside the event horizon, might be simultaneously described as information processing on the black hole's two-dimensional surface. This implies that time inside black holes might operate according to completely different principles than the temporal flow experienced in normal spacetime. As you hurtle toward your appointment with the central singularity, time itself becomes not just distorted but fundamentally meaningless. The mathematics predict that temporal coordinates break down completely at the singularity, where past and future lose all distinction and the concept of when becomes as nonsensical as asking what's north of the North Pole. In your final moments, you discover that time, that most reliable companion throughout your entire existence, has revealed itself as the universe's most treacherous enemy. It has slowed your destruction to give you maximum opportunity to contemplate your fate, accelerated the universe around you to show you everything you're losing, and finally abandoned you entirely to face whatever lies beyond the realm where mathematics itself breaks down. The clocks that once measured your life have become instruments of cosmic torture, counting down to a moment that will never arrive for the outside universe but approaches with mathematical certainty for you. The journey into darkness, what you would actually experience. As time itself transforms from ally to executioner, your senses become the final witnesses to phenomena that no human has ever observed and lived to describe. What unfolds before you transcends every earthly experience, every conceivable preparation for death, and every scientific simulation ever conducted. This is the universe revealing its most closely guarded secrets to someone who can never share them. A cosmic revelation played out in the theater of your own destruction. The journey into darkness becomes simultaneously the most scientifically significant and personally meaningless experience possible, as you witness wonders that redefine the very nature of reality while hurtling toward your inevitable annihilation. The descent begins with a sensation that feels almost mundane: weightlessness. As you surrender to the black hole's gravitational embrace, you experience the same floating sensation that astronauts describe during orbital flights. Einstein's equivalence principle ensures that free fall feels identical to floating in empty space, creating the surreal impression that you're drifting peacefully through the cosmos rather than plummeting toward the universe's most destructive force. This deceptive tranquility masks the fact that you're accelerating at rates that would liquefy any spacecraft ever built, reaching velocities that transform you into a relativistic projectile aimed at the heart of spacetime itself. Your first indication that this journey differs from ordinary space travel comes through your eyes, as the black hole's gravitational field begins warping light in ways that violate every intuitive understanding of optics. The process starts subtly, with slight distortions in the star field that you might initially attribute to equipment malfunction or atmospheric effects. But as you fall deeper into the gravitational well, these distortions intensify into visual phenomena that would have seemed impossible just moments before. Gravitational lensing transforms the familiar constellations into funhouse mirror reflections of themselves. Light from distant stars follows curved paths through the warped spacetime around the black hole, creating multiple images of the same objects appearing in different locations. You might see the same bright star simultaneously above, below, and to either side of you, each image representing photons that took different curved paths through the black hole's gravitational field to reach your eyes. The effect resembles looking through a cosmic kaleidoscope where reality fragments into infinite reflections of itself. As your velocity increases toward significant fractions of light speed, relativistic effects add their own layer of visual horror to the scene. The universe ahead of you undergoes dramatic blue shifting as the Doppler effect compresses light frequencies, causing normally invisible ultraviolet radiation to shift into the visible spectrum while visible light becomes brilliant blue-white. Stars that appeared dim and reddish from a distance now blaze with the intensity of welding torches, their increased brightness threatening to overwhelm your visual system. Behind you, the opposite transformation occurs with equally disturbing results. The cosmos you're leaving becomes increasingly red-shifted, with familiar stellar patterns fading into deep infrared wavelengths that your eyes cannot detect. The Milky Way's spiral arms, once clearly visible as bands of starlight, disappear into darkness punctuated only by the faint glow of extremely red-shifted photons. You watch your home galaxy fade from view not through distance, but through the relativistic transformation of light itself. The approach to 90% of light speed unleashes Einstein's most counterintuitive visual predictions. The entire star field ahead of you contracts into an ever-narrowing cone of brilliant light due to relativistic beaming, the tendency for photons to concentrate in your direction of motion. What once filled your entire forward vision becomes compressed into a ring of blazing light that grows brighter and more compact as your speed increases. This ring eventually contains the blue-shifted radiation from every star, galaxy, and cosmic structure ahead of you, compressed into a band that could fit within your outstretched hand. If the black hole possesses an accretion disk, a spiral of superheated matter spiraling inward at nearly light speed, you witness one of the universe's most spectacular and deadly light shows. The disk appears as a vast, flat cloud of million-degree plasma glowing with the combined light of 1 trillion stars. Magnetic field lines, made visible by the charged particles spiraling along them, create ethereal structures that twist and dance through the disk like cosmic aurora. The entire structure rotates with hypnotic beauty, each orbit bringing matter closer to the point of no return, while generating X-rays and gamma radiation intense enough to sterilize entire star systems. The mathematics governing these visual phenomena reveal why the journey becomes increasingly surreal.
Photon orbits around black holes follow geodesics described by the equation dx mi dtaf, gamma mi alpha vita, dx alpha dtaf, dx vita dtaf, mi then, where the Christoffel symbols gamma mi alpha vita encode the curvature of space-time.
These equations predict the existence of photon spheres, circular orbits where light can theoretically orbit the black hole indefinitely, creating multiple images of distant objects that arrive at your location from seemingly impossible directions. As you approach the event horizon, assuming you've won the cosmic lottery of encountering a supermassive black hole that allows you to cross intact, the visual phenomena reach crescendo intensity. Every photon from the universe outside becomes gravitationally lensed into what physicists call the Einstein ring, a brilliant circle that appears to contain the compressed image of the entire cosmos. Within this ring, you witness accelerated cosmic evolution as time dilation effects cause the outside universe to appear to speed up dramatically. The crossing of the event horizon itself provides one of physics' most anticlimactic moments. Despite representing the universe's most fundamental boundary, the point beyond which no information can ever escape, the actual crossing feels utterly unremarkable. There's no cosmic fanfare, no sudden change in sensation, no dramatic moment marking your transition into the realm of no return. For supermassive black holes, you simply continue falling through what appears to be empty space, with no local indication that you've crossed the most significant boundary in the known universe. But the universe outside begins exhibiting increasingly bizarre behavior due to extreme gravitational effects. Light that was emitted by distant stars millions of years ago continues reaching you, but highly redshifted and distorted by its journey through increasingly curved spacetime. The Einstein ring behind you, containing the compressed image of everything you're leaving behind, begins showing you the accelerated future of the cosmos as time dilation effects compress millions of years of stellar evolution into moments of your subjective experience. NASA's 2024 supercomputer simulations of the journey inside a supermassive black hole reveal a landscape that defies human imagination. The interior space, while doomed to collapse toward the central singularity, initially appears vast and strangely beautiful. Spacetime geometry inside the event horizon creates optical illusions where distances become impossible to judge and directions lose their conventional meaning. Light from the outside universe, trapped and circulating within the black hole's interior, creates ethereal illumination that has never been seen by human eyes. During your final 12.8 seconds of survival inside a Milky Way equivalent black hole, or the hours you might experience in larger supermassive monsters, you become the universe's ultimate scientific observer, witnessing phenomena that exist nowhere else in the cosmos. Tidal forces, while eventually lethal even in supermassive black holes, initially remain gentle enough to allow conscious observation of your surroundings. You experience the strangest sensation in physics, falling toward a point where the very concept of falling loses meaning as space and time exchange roles. The approach to the central singularity unleashes the universe's most extreme physics. Space-time curvature grows without bound, creating tidal forces that eventually overwhelm even the gentlest supermassive black holes. But before your destruction, you witness the breakdown of physics itself as general relativity approaches its limits. The mathematical singularity represents not just infinite density but infinite space-time curvature, a point where the equations that describe reality simply stop providing meaningful answers. Modern theoretical physics suggests your final moments might involve phenomena that transcend current understanding. Loop quantum gravity predicts that quantum effects might prevent true singularities from forming, potentially creating bounces that could theoretically transform the black hole into a white hole ejecting matter back into the universe. String theory proposals include fuzzball structures that replace the central singularity with extended stringy geometries. These remain speculative, but they suggest that your ultimate fate might involve physics more exotic than simple gravitational collapse. The holographic principle implies that your entire journey, every sensation, every observation, every final thought, becomes encoded as information on the black hole's two-dimensional event horizon surface. From this perspective, your three-dimensional experience of falling inward might be simultaneously described as quantum information processing occurring on the boundary itself, creating a duality between your subjective experience and the mathematical description of black hole physics. Your final sensations depend critically on the black hole type that claimed you. For stellar mass monsters, the journey ends in violent spaghettification before you can witness the exotic physics inside. But for supermassive giants, you become cosmology's ultimate experimental subject, experiencing gravitational effects that exist nowhere else in the universe while approaching a singularity where the known laws of physics break down completely. The last thing you might observe, according to some theoretical models, could be the universe itself undergoing fundamental transformation as you approach the singularity. Quantum gravity effects might create closed time-like curves where causality breaks down, allowing you to observe events that precede their causes. Space and time might exchange roles completely, making spatial coordinates temporal and temporal coordinates spatial in ways that have no analog in normal physics. As consciousness fades, whether from spaghettification, extreme tidal forces, or encounter with the singularity itself, you carry with you observational data that could revolutionize human understanding of the universe. You have witnessed the universe's most extreme gravitational fields, observed matter and energy under conditions that cannot be reproduced in any laboratory, and experienced space-time curvature approaching the theoretical maximum allowed by general relativity. But the cosmic tragedy of this journey lies in its ultimate futility. Every discovery you make, every phenomenon you observe, every breakthrough insight into the nature of reality dies with you behind the event horizon. The universe's most significant scientific observations become its most perfectly kept secrets, known only to the mathematical formalism that describes black hole interiors and the unfortunate observers who can never share their discoveries. Your journey into darkness illuminates the deepest mysteries of physics while ensuring that no one else can ever benefit from that illumination. You become both the universe's greatest scientific explorer and its most isolated prisoner, witnessing wonders beyond imagination while trapped forever beyond the boundary that separates the knowable from the unknowable. The darkness you enter contains light that no external observer will ever see, revealing truths that will never be told. Inside the forbidden zone, life beyond the event horizon. Yet that darkness conceals the universe's most profound secret, a realm where the fundamental rules of reality have been rewritten by gravity so extreme that space and time themselves exchange roles. Inside the forbidden zone beyond the event horizon, you enter a domain that exists by different laws than the rest of the cosmos. A place where up and down lose all meaning, where every possible path leads to the same inevitable destination, and where the very concept of escape becomes as meaningless as traveling backward through time. Here, in this cosmic prison that makes Alcatraz look like an open door, you discover that crossing the event horizon hasn't just separated you from the outside universe. It has exiled you to a realm where physics operates according to principles so alien that they challenge the very notion of what it means to exist. The first revelation of life inside the event horizon strikes with deceptive subtlety. Nothing seems different. For supermassive black holes, the crossing feels so unremarkable that you might initially believe some error in calculation has occurred, that perhaps you haven't actually crossed the point of no return. The space around you appears ordinary, even spacious, with no walls, barriers, or obvious signs of imprisonment. You continue falling through what seems like empty vacuum, breathing normally if you have life support, thinking clearly, observing your surroundings with the same senses that served you throughout your previous existence. But this apparent normalcy masks a transformation in the fundamental geometry of spacetime so profound that it defies human intuition. Inside the event horizon, the mathematical descriptions of space and time undergo what physicists call a coordinate transformation that sounds clinical but represents one of the most radical restructurings possible in the known universe. The radial coordinate, the dimension that in normal space allows movement toward or away from the black hole's center, becomes time-like rather than space-like. This geometric metamorphosis creates consequences that read like cosmic horror fiction. In normal spacetime, you can choose your direction of movement through the three spatial dimensions: left or right, forward or backward, up or down. While you cannot control your movement through time, you age whether you want to or not, you retain freedom of spatial movement. Inside a black hole, this relationship inverts with terrifying completeness. Falling toward the central singularity becomes as inevitable as aging, while your movement through time becomes as arbitrary as your previous spatial choices. The mathematics governing this nightmare scenario emerge from Einstein's field equations applied to the interior of black holes. The Schwarzschild metric, when extended beyond the event horizon using coordinates that remain well-behaved at the boundary, reveals that all future-directed time-like curves, all possible paths you could take through spacetime while moving forward in time, converge inexorably toward the central singularity. No amount of rocket thrust, regardless of its magnitude, can alter this geometric fact any more than rocket engines could prevent you from aging in normal space. General relativity provides specific timescales for this doomed journey that vary dramatically with black hole mass. For stellar mass monsters like Cygnus X1, you have approximately 0.0001 seconds from event horizon to singularity, barely enough time for electrical signals to travel through your nervous system, let alone for conscious contemplation of your predicament. Intermediate mass black holes offer slightly more generous death sentences, typically measured in milliseconds rather than fractions of milliseconds. But supermassive black holes transform this rush toward oblivion into something resembling a philosophical meditation on existence itself. NASA's detailed simulations show that inside a Milky Way equivalent black hole, you survive approximately 12.8 seconds from horizon crossing to singularity encounter, an eternity compared to stellar mass timeframes. More sophisticated trajectory analysis reveals that optimal initial conditions could extend this survival time to several hours for the largest supermassive black holes, providing unprecedented opportunity to observe physics operating under the most extreme conditions in the universe. During these precious moments or hours, you experience phenomena that exist nowhere else in the cosmos. The approach to the singularity subjects you to ever-increasing tidal forces that initially remain below the threshold of perception but grow exponentially as you fall deeper into the gravitational well. Even in supermassive black holes, where the event horizon crossing felt gentle, the mathematics eventually demand your destruction as spacetime curvature grows without bound. The visual experience inside the event horizon defies every earthly reference point. Light from the outside universe, gravitationally lensed by the extreme spacetime curvature, creates optical phenomena that have no terrestrial analog. The compressed image of the entire external cosmos appears as a brilliant ring that gradually shrinks as you fall deeper, showing you the accelerated evolution of everything you're leaving behind due to extreme time dilation effects. But perhaps most disturbing of all is the realization that your imprisonment operates through pure geometry rather than physical barriers. There are no walls confining you, no force fields preventing escape, no cosmic guardians ensuring your captivity. Instead, the very structure of spacetime has been so severely warped that every direction you could possibly travel leads deeper into the gravitational well. The event horizon represents not a physical boundary but a geometric point of no return where the topology of spacetime itself ensures your doom. Recent theoretical developments have revealed that the interior of black holes might contain physics even stranger than classical general relativity predicts. The firewall hypothesis, proposed by physicists studying the intersection of quantum mechanics and gravity, suggests that the event horizon might be surrounded by a wall of high-energy particles that would incinerate approaching objects instantly. This theoretical firewall would transform the gentle crossing predicted by classical physics into a violent encounter with temperatures approaching the Planck scale, 10 superscript 3 superscript 2 Kelvin, hot enough to vaporize not just matter but the very concepts of matter and energy. Alternative theories propose that black hole interiors might contain exotic structures predicted by quantum gravity. String theory's fuzzball conjecture suggests that the classical interior spacetime might be replaced by extended stringy structures that store information in quantum microstates, eliminating the central singularity while preserving the thermodynamic properties that Hawking calculated for black holes. These fuzzballs would create a completely different experience for infalling observers, potentially involving interactions with quantum geometry at scales far smaller than atomic nuclei. Loop quantum gravity calculations indicate that the approach to the central singularity might involve quantum geometric effects that prevent infinite curvature from forming. Instead of encountering a mathematical singularity where physics breaks down, you might experience a quantum bounce that could theoretically transform the black hole into a white hole, a hypothetical object that ejects matter and energy back into the universe. Recent 2025 research suggests that this transformation might occur through mechanisms involving unimodular gravity, potentially making black holes cosmic recycling centers rather than permanent prisons. The holographic principle adds another layer of strangeness to the experience of life inside the event horizon. If this fundamental concept in theoretical physics is correct, then your entire three-dimensional journey through the black hole's interior might be simultaneously described as information processing occurring on the two-dimensional surface of the event horizon. This holographic duality suggests that your subjective experience of falling inward could be mathematically equivalent to quantum computations performed on the boundary itself. Google's 2022 quantum computer experiment demonstrating holographic wormholes using the SYK model provides laboratory evidence for these exotic possibilities. While performed in simplified toy models rather than realistic black hole geometries, these experiments suggest that the interior of black holes might be connected to other regions of spacetime through quantum entanglement, creating the possibility that your journey into the forbidden zone might actually constitute passage through a cosmic tunnel connecting distant parts of the universe. The ER equals EPR correspondence, proposed by physicists studying the relationship between quantum entanglement and spacetime geometry, suggests that Einstein-Rosen bridges, wormholes, might be geometrically equivalent to Einstein-Podolsky-Rosen entanglement. If this correspondence reflects physical reality, then black hole interiors might serve as cosmic transportation networks rather than simple gravitational death traps, potentially allowing information, or even matter, to emerge in distant regions of spacetime. As you approach the central singularity, classical general relativity predicts the breakdown of physics itself. The spacetime curvature grows without bound, creating tidal forces that exceed any finite value and densities that approach mathematical infinity. At this point, Einstein's field equations cease to provide meaningful predictions, and the mathematical framework that successfully describes the rest of the universe simply stops working. But quantum gravity theories suggest that this classical breakdown might mask physics more exotic than simple gravitational collapse. The approach to the Planck scale, where quantum effects become comparable to gravitational effects, might reveal entirely new physics involving the fundamental structure of spacetime itself. Some theories predict that space and time might emerge from more fundamental quantum mechanical processes, suggesting that your encounter with the singularity could involve direct interaction with the underlying quantum foam from which spacetime crystallizes. Modern developments in black hole thermodynamics reveal connections between event horizons and the fundamental arrow of time that governs entropy increase throughout the universe. Your journey into the forbidden zone contributes to the universe's total entropy, making your destruction not just a personal tragedy, but a cosmic inevitability written into the second law of thermodynamics. The information you carry, every memory, every quantum state, every bit of data that defines your existence, either vanishes forever in violation of quantum mechanics or becomes permanently encoded in ways that preserve unitarity while making retrieval impossible. The most recent theoretical breakthroughs suggest that time inside black holes might operate according to completely different principles than the temporal flow experienced in normal spacetime. Some models predict the existence of closed time-like curves where effects can precede their causes, creating causal paradoxes that challenge fundamental assumptions about the nature of reality. Others propose that the interior might contain regions where past and future become indistinguishable, creating a timeless realm where the concepts of before and after lose all meaning. As your survival time inside the Forbidden Zone approaches its inevitable end, you face the ultimate confrontation with the limits of human knowledge. The singularity represents not just infinite density and infinite spacetime curvature, but the complete breakdown of the conceptual framework that humans use to understand reality. At this point, you encounter physics so extreme that it might involve principles completely alien to terrestrial experience: quantum gravity, extra dimensions, fundamental modifications to the nature of space and time itself. Your final moments inside the event horizon mark the end of the most extraordinary scientific journey possible. A voyage to the very limits of the knowable universe, where mathematics breaks down and new physics begins. You have become cosmology's ultimate experimental subject, experiencing gravitational effects that exist nowhere else while approaching the boundary between the physics we understand and the physics we can only dream about. But the tragic irony of life inside the Forbidden Zone remains absolute. Every discovery you make, every observation you record, every insight into the fundamental nature of reality dies with you behind the event horizon. The cosmic prison that gravity has constructed operates with perfect efficiency, ensuring that the universe's most significant scientific discoveries remain forever hidden behind the veil that separates the knowable from the unknowable. The Forbidden Zone keeps its secrets with absolute fidelity, making you both witness and victim of the universe's deepest mysteries. The information paradox. Where do you go when you die? But the universe's perfect secret-keeping raises a question so fundamental that it threatens to unravel the very foundations of physics itself. When you die inside a black hole, where does the information that defines your existence actually go? This isn't merely a philosophical inquiry about consciousness or soul. It's a scientific crisis that strikes at the heart of quantum mechanics and challenges everything we thought we understood about the conservation of information in the universe. Your death inside the event horizon doesn't just represent the end of a single human life. It potentially violates the most sacred principles of quantum physics, creating a paradox so profound that it has tormented the world's greatest physicists for nearly 5 decades and continues to spawn revolutionary theories that rewrite our understanding of reality itself. The crisis began in 1975 when Stephen Hawking published calculations that would forever change how physicists think about black holes and information. Using the principles of quantum field theory in curved spacetime, Hawking demonstrated that black holes aren't perfectly black but actually emit thermal radiation, now known as Hawking radiation, through quantum mechanical processes occurring just outside the event horizon. Virtual particle pairs, constantly popping into existence throughout empty space, occasionally appear so close to the event horizon that one particle falls in while the other escapes, creating a slow leak of energy that causes black holes to gradually evaporate over enormous timescales. For stellar mass black holes, this evaporation process unfolds over periods that dwarf cosmic history itself. A black hole with the mass of our Sun would take approximately 10 years to completely evaporate, a time span so vast that it exceeds the current age of the universe by a factor of 10. Even the smallest possible black holes, containing just a few times the mass of Mount Everest, would require 10^1 years to disappear completely. These numbers represent timescales so enormous that they render Hawking evaporation essentially irrelevant for any practical purposes. Yet they create theoretical implications that shake the foundations of physics. The paradox emerges from the mathematical properties of Hawking radiation itself. Hawking's calculations show that this radiation appears to be perfectly thermal, random electromagnetic energy with no correlation to the matter and information that originally fell into the black hole. If you fall into a black hole and the black hole subsequently evaporates completely through Hawking radiation, the mathematics suggest that every bit of information that defined your existence, every quantum state of every particle in your body, every memory encoded in your neural connections, every unique pattern that distinguished you from empty space would be permanently destroyed. This apparent destruction of information violates one of quantum mechanics' most fundamental principles: unitarity. In quantum physics, information cannot be created or destroyed, only transformed from one form to another. Every quantum mechanical process, no matter how complex, must preserve the total amount of information in the universe. When particles collide, atoms decay, or stars explode, the information describing these systems changes form but never disappears. The principle of unitarity ensures that the universe's total information content remains constant throughout all physical processes. But Hawking's original calculations suggested that black hole evaporation creates an exception to this universal rule. If information can be permanently destroyed by falling into black holes, then quantum mechanics is fundamentally wrong, or at least incomplete. This contradiction between general relativity, which predicts that information falling into black holes disappears forever, and quantum mechanics, which demands that information must be conserved, became known as the black hole information paradox, and it has driven theoretical physics research for nearly half a century. The stakes of this paradox extend far beyond academic curiosity. If information can be destroyed in black holes, then the deterministic nature of quantum mechanics breaks down, making the universe fundamentally unpredictable in ways that violate every successful theory of physics. The equations that describe atomic structure, chemical bonding, stellar fusion, and even the quantum computers that may eventually solve this paradox all depend on information conservation. Discovering that black holes destroy information would force physicists to rebuild quantum mechanics from the ground up, potentially invalidating decades of scientific progress. Early attempts to resolve the paradox focused on finding mechanisms that could allow information to escape from black holes without violating general relativity. Some physicists proposed that Hawking radiation might carry subtle correlations that encode information about infalling matter, making the radiation only appear thermal while actually containing encrypted data about everything the black hole has consumed. Others suggested that information might be stored on the event horizon surface itself, preserved in microscopic fluctuations that could theoretically be decoded by sufficiently advanced observers. The most radical early proposal came from Leonard Susskind and Gerard T. Hooft, who developed the holographic principle, the revolutionary idea that all information inside a black hole can be encoded on its two-dimensional event horizon surface. According to this principle, your three-dimensional fall into the black hole would be simultaneously described as information processing occurring on the boundary itself, creating a holographic duality where the same physics can be described from two completely different perspectives. The holographic principle suggests that when you fall into a black hole, you don't actually disappear into a three-dimensional interior. Instead, your information becomes encoded as patterns on the event horizon surface, preserved in a form that maintains quantum mechanical unitarity while appearing to external observers as if you've been absorbed by the black hole. This creates a fundamental duality. From your perspective, you fall through the event horizon and experience the interior spacetime, but from the boundary perspective, you become part of a two-dimensional holographic description that never crosses the horizon. Recent theoretical breakthroughs have provided increasingly convincing evidence that the holographic principle offers the correct resolution to the information paradox. The ADS/CFT correspondence, discovered by Juan Meldacena in 1997 and celebrating its 25th anniversary in 2022, demonstrates mathematically rigorous examples of holographic duality in simplified spacetimes. These calculations show how three-dimensional gravitational theories correspond exactly to two-dimensional boundary field theories, providing concrete proof that holographic descriptions can capture all the physics of gravitational systems. Google's groundbreaking 2022 quantum computer experiment created the first laboratory demonstration of holographic wormholes using the SYK, Suchdev-Yekitaev model. While performed in a highly simplified system with just 9 quantum bits, this experiment successfully demonstrated quantum teleportation through a simulated wormhole structure, providing proof-of-principle evidence for the ER=EPR conjecture, the revolutionary idea that Einstein-Rosen bridges, wormholes, correspond to Einstein-Podolsky-Rosen entanglement. The most significant recent development came through the discovery of quantum error correction in holographic systems. Physicists realized that the mathematical structure of ADS/CFT correspondence naturally implements quantum error-correcting codes, where information encoded on the boundary can be reconstructed even if parts of the bulk spacetime are corrupted or destroyed. This discovery reveals that black holes might function as cosmic quantum computers, processing information through gravitational dynamics while preserving unitarity through holographic encoding. The island formula and page curve calculations, developed since 2019, provide the mathematical framework for understanding how information escapes from evaporating black holes. These calculations show that when quantum extremal surfaces called islands are included in the entropy calculations, the page curve emerges naturally. Information initially appears to be lost as the black hole grows, but begins returning to the external universe when the black hole reaches half its maximum size and starts evaporating faster than it accretes new matter. Multiple research papers published throughout 2024 and 2025 have confirmed this behavior across various black hole types and space-time geometries, suggesting a universal resolution to the information paradox. The mathematics indicate that information falling into black holes becomes temporarily hidden but not permanently destroyed, eventually returning to the external universe through subtle correlations in the Hawking radiation emitted during the final stages of black hole evaporation. For someone falling into a black hole, these theoretical developments paint a picture that borders on the metaphysical. Your information, every quantum bit that defines your physical existence, doesn't disappear when you cross the event horizon. Instead, it becomes encoded in the holographic description of the black hole's boundary, preserved in a form that maintains the fundamental principles of quantum mechanics while appearing to be lost from the perspective of classical general relativity. The process operates through mechanisms so subtle that they challenge human intuition about identity and existence. Your information becomes scrambled with that of every other object that has ever fallen into the black hole, creating a quantum-entangled state that spans the entire event horizon surface. This scrambling occurs through gravitational dynamics that operate as a form of quantum computation, processing information through the complex gravitational interactions that govern black hole physics. Recent developments in quantum gravity suggest that your death inside a black hole might involve physics even more exotic than simple information preservation. Some theories predict that the interior of black holes might contain closed time-like curves where your information could interact with itself at different temporal coordinates, creating causal loops that challenge conventional notions of cause and effect. Others propose that the central singularity might be replaced by quantum geometric structures that preserve information through mechanisms involving extra dimensions or fundamental modifications to spacetime geometry. The firewall hypothesis, proposed by Elmhirey, Merolf, Polchinski, and Sully in 2012, suggests that the information paradox might be resolved through violent physics at the event horizon itself. According to this proposal, the quantum entanglement required to preserve information creates a wall of high-energy particles at the event horizon that would incinerate infalling observers instantly. This firewall would ensure that no observer ever experiences the classical interior spacetime, eliminating the apparent contradiction between the boundary and bulk descriptions of black hole physics. But the majority of leading researchers favor complementarity solutions that preserve the equivalence principle for infalling observers while maintaining information conservation through holographic mechanisms. These approaches suggest that you would experience a normal infall and classical interior spacetime while your information simultaneously remains encoded on the boundary in a scrambled but recoverable form. The ultimate fate of your information depends on the black hole's eventual evaporation through Hawking radiation. As the black hole shrinks and its temperature increases, the correlations in the outgoing radiation become increasingly complex, eventually encoding enough information to reconstruct everything that ever fell into the black hole, including you. This process operates through quantum mechanical mechanisms so sophisticated that they might require technologies far beyond current human capabilities to decode. But the fundamental principle of information conservation ensures that nothing is truly lost. Modern quantum computers have begun simulating aspects of this information recovery process, demonstrating how quantum error correction codes naturally emerge from gravitational dynamics in holographic systems. IBM's quantum computers have successfully reproduced page curves in simplified models, showing how information initially appears to be lost but eventually returns through quantum correlations in the outgoing radiation. The resolution of the information paradox reveals that your death inside a black hole represents not the destruction of your information but its transformation into the most complex quantum state possible. You become part of a cosmic quantum computer that processes information through gravitational dynamics, preserving every detail of your existence in a form so scrambled that it approaches the theoretical limits of quantum complexity. In this view, black holes emerge not as cosmic destroyers but as cosmic librarians, cataloging and preserving every bit of information that falls into them while processing this information through gravitational computations that span cosmological timescales. Your journey into the black hole transforms you from a classical object into quantum information, ensuring that while your subjective experience ends at the singularity, the information that defined your existence persists forever in the quantum mechanical description of the universe. The paradox that began with the simple question of where you go when you die has revealed that death itself might be an illusion created by the classical approximation to quantum gravity, hiding deeper truths about the nature of information, identity, and existence in a universe governed by quantum mechanical principles. Theoretical escapes. Wormholes, white holes, and wild possibilities. Yet even as quantum mechanics suggests that your information might survive in some scrambled cosmic library, a growing chorus of theoretical physicists whispers of possibilities so extraordinary they border on science fiction. What if black holes aren't cosmic death traps at all, but gateways to realms beyond our imagination? Hidden within the most exotic corners of theoretical physics lie proposals that could transform your terrifying plunge into a black hole from a journey toward annihilation into passage through the universe's most incredible transportation network. These aren't the fantasies of science fiction writers, but serious theoretical constructs emerging from the cutting edge of quantum gravity research, wormholes that tunnel through space-time itself, white holes that eject matter across cosmic distances, and quantum mechanical phenomena so strange that they suggest reality operates according to principles far more extraordinary than even Einstein dared imagine. The most tantalizing possibility emerges from one of Einstein's own discoveries, hidden within his 1935 collaboration with Nathan Rosen. Working through the mathematics of general relativity, Einstein and Rosen discovered that the equations permitted the existence of bridges connecting distant regions of spacetime, structures that would later become known as Einstein-Rosen bridges, or, more dramatically, wormholes. These theoretical tunnels through the fabric of space and time could potentially connect black holes to distant parts of our universe, or even to entirely separate universes existing in parallel dimensions. The mathematics governing these cosmic shortcuts appear deceptively elegant. The Einstein-Rosen bridge represents a solution to Einstein's field equations that extends the geometry of black holes beyond the central singularity, creating a tunnel that emerges as a white hole in another region of spacetime. Unlike black holes, which allow matter and energy to flow inward but never outward, white holes would operate as cosmic fountains, ejecting matter and energy with such violence that nothing could ever fall into them from the outside. Modern physicists studying wormhole physics have discovered that these structures face seemingly insurmountable challenges that prevent them from serving as viable transportation networks. Classical wormholes, as described by general relativity alone, suffer from catastrophic instability. They collapse faster than light could travel through them, making passage impossible for any material object. The throat of the wormhole pinches off in microseconds, severing the connection between its two mouths and trapping anything attempting the journey in a region of spacetime that rapidly contracts to zero volume. But quantum mechanics might provide the key to stabilizing these cosmic tunnels. Theoretical calculations suggest that exotic matter with negative energy density could prop open wormhole throats, preventing their collapse and allowing safe passage between distant regions of space and time. This exotic matter would need to violate the averaged null energy condition, a fundamental requirement that energy density remain positive when averaged along light-like paths, creating regions of spacetime where gravity effectively repels rather than attracts. The Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948, demonstrates that quantum mechanics can indeed create regions of negative energy density. When two parallel metal plates are placed extremely close together in empty space, quantum vacuum fluctuations between the plates create less energy than exists in the vacuum outside, generating a net negative energy density that pushes the plates together. While the Casimir effect produces only tiny amounts of negative energy, it proves that the exotic matter required for wormhole stabilization doesn't violate fundamental physical principles. Recent theoretical breakthroughs have revealed deep connections between wormholes and quantum entanglement that suggest these cosmic tunnels might be far more common than previously imagined. The ER equals EPR correspondence, proposed by one Meldesena and Leonard Susskind, posits that Einstein-Rosen bridges, wormholes, are geometrically equivalent to Einstein-Podolsky-Rosen entanglement, quantum correlations between particles. This revolutionary conjecture suggests that every pair of quantum-entangled particles might be connected by a microscopic wormhole, making these space-time tunnels fundamental features of quantum mechanics rather than exotic curiosities. Google's groundbreaking 2022 quantum computer experiment provided the first laboratory evidence supporting the ER equals EPR correspondence. Using a simplified model called the SYK, Suchdev-Yekitaev, system implemented on a 9-qubit quantum processor, researchers successfully demonstrated quantum teleportation through a simulated holographic wormhole. While performed in a highly idealized system that bears little resemblance to realistic black holes, this experiment proved that wormhole-like structures can emerge naturally from quantum mechanical processes. The implications for your journey into a black hole are staggering. If the ER equals EPR correspondence reflects physical reality, then the black hole you're falling into might be quantum entangled with distant regions of spacetime, creating microscopic wormhole connections that could theoretically allow information or even matter to escape the gravitational prison. Your death inside the event horizon might trigger quantum correlations that transport aspects of your existence to entangled regions elsewhere in the universe, making your destruction simultaneously your liberation. Even more extraordinary possibilities emerge from recent developments in loop quantum gravity, a theoretical framework that attempts to quantize spacetime itself at the smallest possible scales. Calculations published in 2025 suggest that quantum geometric effects might prevent the formation of classical singularities inside black holes, replacing them with quantum bounces that could transform black holes into white holes after periods of internal evolution lasting millions or billions of years. According to these radical proposals, your encounter with what appears to be a classical singularity might actually involve interaction with quantum spacetime geometry operating at the Planck scale. Distances of 10^3 meters where space and time lose their continuous character and become granular, like pixels in a cosmic computer simulation. At these scales, the infinite curvature predicted by classical general relativity gets smoothed out by quantum effects, creating a bridge that connects the black hole's interior to a white hole in another region of spacetime. The University of Sheffield's March 2025 research suggests that this transformation might occur through mechanisms involving unimodular gravity, where the cosmological constant becomes a dynamical field rather than a fixed parameter. Their calculations indicate that black holes might undergo phase transitions that convert them into white holes, potentially ejecting all the matter and information they've accumulated over cosmic history back into the universe in violent explosive events. String theory, the leading candidate for a theory of quantum gravity, predicts even more exotic possibilities for escape from black holes. The fuzzball conjecture, developed by Samir Mather and colleagues, suggests that black holes might not contain classical interior spacetime at all. Instead, the region inside the event horizon could be filled with extended stringy structures that store information in quantum microstates, eliminating the central singularity while preserving all the thermodynamic properties that Hawking calculated. If the fuzzball conjecture is correct, your journey into a black hole would involve interaction with quantum geometry on scales far smaller than atomic nuclei. Rather than encountering a point-like singularity, you would experience a complex quantum system that preserves information through stringy dynamics operating in multiple dimensions beyond the familiar 3 of space and 1 of time. Your destruction would transform into absorption by a quantum mechanical system so complex that it might constitute a form of cosmic consciousness operating according to principles completely alien to terrestrial experience. The holographic principle adds yet another layer of strangeness to potential escape mechanisms. If black holes are indeed holographic systems where three-dimensional interior physics corresponds to two-dimensional boundary dynamics, then your fall into the black hole might be simultaneously described as information processing occurring on the event horizon surface. From this perspective, you never actually enter the black hole's interior. Instead, you become part of a holographic projection that preserves all the physics of infall while keeping your information safely encoded on the boundary. Recent developments in ADS/CFT correspondence have revealed that holographic systems naturally implement quantum error correction codes, where information encoded on the boundary can be reconstructed even if parts of the bulk spacetime are corrupted or destroyed. This suggests that black holes might function as cosmic quantum computers, processing information through gravitational dynamics while maintaining the ability to reconstruct interior physics from boundary data. The firewall hypothesis proposes perhaps the most violent form of escape from black hole death. According to this controversial theory, the quantum entanglement required to preserve information creates a wall of high-energy particles at the event horizon that incinerates approaching objects instantly. While this firewall would certainly prevent you from experiencing the classical interior spacetime, it would also vaporize you at temperatures approaching the Planck scale, 10^3 Kelvin, hot enough to break down the fundamental particles of matter into their constituent quantum components. Some physicists have proposed that the firewall might actually serve as a liberation mechanism, transforming infalling matter into pure energy that escapes the black hole as Hawking radiation. Your encounter with the firewall would convert your mass energy into thermal photons that eventually reach distant observers, carrying scrambled information about your quantum state in subtle correlations that preserve unitarity while appearing to destroy classical information about your identity. The most speculative possibilities emerge from theories that attempt to unify quantum mechanics with gravity through mechanisms involving extra dimensions, time travel, or fundamental modifications to the nature of spacetime itself. Some models predict that black holes might contain closed time-like curves where you could interact with your own past, creating causal loops that challenge conventional notions of cause and effect. Others suggest that the interior might connect to baby universes that bud off from our spacetime, allowing escape through dimensional transitions that have no analog in normal physics. Quantum cosmology models propose that black holes might serve as wombs for new universes, with the Big Bang representing the white hole phase of black hole formation in a parent universe. If these models are correct, your journey into a black hole might contribute to the birth of entirely new cosmos, making your death simultaneously the genesis of billions of future worlds populated by civilizations that will never know they owe their existence to your cosmic sacrifice. The most recent theoretical developments suggest that even the concept of escape might be fundamentally misleading when applied to black hole physics. If space and time emerge from more fundamental quantum mechanical processes, as proposed by emergent gravity theories, then your encounter with a black hole might involve direct interaction with the underlying quantum substrate from which spacetime crystallizes. At this level, the distinction between inside and outside, past and future, existence and non-existence might lose all meaning in ways that make classical concepts of escape irrelevant. Modern quantum computers are beginning to simulate aspects of these exotic escape mechanisms, demonstrating how quantum information can tunnel through barriers that would be impenetrable in classical physics. IBM's quantum processors have reproduced page curves showing how information initially appears to be lost but eventually returns through quantum correlations, while Google's quantum computer created the first artificial wormhole using holographic principles. These theoretical possibilities transform the simple question of whether you can escape from a black hole into a profound inquiry about the nature of reality itself. They suggest that your journey into apparent doom might actually represent passage through the universe's most sophisticated transportation network, one that operates according to principles so advanced that they transcend human understanding of space, time, causality, and existence. Yet, for all their mathematical beauty and theoretical sophistication, these escape mechanisms remain unproven speculations that emerge from the bleeding edge of theoretical physics. No experiment has ever demonstrated traversable wormholes, observed white hole formation, or detected the exotic matter required to stabilize space-time tunnels. The universe guards its deepest secrets jealously, revealing them only through mathematical equations that describe phenomena far beyond the reach of current technology to observe or test. Your fall into a black hole might indeed represent passage through a cosmic gateway to realms beyond imagination, but it might also constitute nothing more than a very exotic form of death, transformed by quantum mechanics into information processing rather than simple annihilation. The universe keeps its ultimate secrets behind the event horizon, where theory and reality converge in ways that no external observer can ever verify. The greatest escape of all might be the liberation from needing to know the answer, as you become part of the cosmic mystery itself. The real black hole's what we've actually observed. But while theorists spin elegant mathematical tales of cosmic gateways and quantum liberation, the universe itself has begun revealing its black hole secrets through methods far more direct and infinitely more dramatic than abstract equations. We have finally learned to see the unseeable, to photograph the unphotographable, and to hear the unhearable songs of spacetime itself as it screams under the most extreme gravitational violence imaginable. In an extraordinary convergence of human ingenuity and cosmic timing, the early 21st century has witnessed the transformation of black holes from purely theoretical constructs into observed realities, captured in stunning photographs that show the very boundaries of spacetime and detected through gravitational waves that carry the death cries of monsters colliding across the cosmos. These discoveries reveal not just that black holes exist, but that they exist in forms and numbers that challenge our understanding of how the universe operates, creating a new astronomy where the invisible becomes visible and the impossible becomes inevitable. The revolution began on April 10, 2019, when humanity first gazed upon the face of a cosmic monster. The Event Horizon Telescope, a planet-sized virtual instrument created by linking radio telescopes from Hawaii to Antarctica, released the first direct image of a black hole's event horizon, revealing the supermassive monster lurking at the heart of the galaxy M87. The photograph showed exactly what Einstein's equations had predicted: a bright ring of glowing matter surrounding a dark central region where light itself cannot escape, creating what scientists call the shadow of the black hole against the brilliant backdrop of its accretion disk. This historic image captured more than just photons from 55 million light-years away. It crystallized a century of theoretical physics into visual reality. The ring measured 42 microarcseconds across, an angular size so small that it would be equivalent to photographing a donut on the moon from Earth. Yet within this tiny circle lay confirmation of spacetime curvature so extreme that it bends light around the black hole's event horizon, creating multiple images of the swirling matter that spirals toward oblivion at nearly the speed of light. M87's central black hole revealed itself as a monster beyond human scale, containing 5 billion times the mass of our Sun compressed into a region spanning 19.5 billion kilometers. So vast that Neptune's entire orbit around the Sun could fit comfortably inside its event horizon. The accretion disk surrounding this gravitational leviathan glows at temperatures exceeding 1 billion degrees, fed by matter torn from nearby stars, and heated to incandescence by magnetic fields millions of times stronger than Earth's. Jets of plasma accelerated to 99% of light speed shoot from the black hole's polar regions, extending for thousands of light years and illuminating entire galaxies with their relativistic fury. 3 years later, the Event Horizon Telescope achieved an even more remarkable feat by imaging Sagittarius A*, the supermassive black hole residing at the heart of our own Milky Way galaxy. This cosmic neighbor, located just 26,000 light-years from Earth, presented unique challenges that pushed observational astronomy to its absolute limits. Unlike M87's relatively stable giant, Sagittarius A* varies on timescales of minutes rather than days, as matter orbits its 4.3 million solar mass bulk in frantically tight spirals that complete full rotations in less than an hour. The resulting image revealed a glowing ring structure remarkably similar to M87's shadow, confirming that supermassive black holes across the universe share fundamental characteristics predicted by general relativity. Yet Sagittarius A* also displayed distinctive features that provide unique insights into black hole physics. The rapid variability of its accretion flow creates a dynamic environment where magnetic field lines snap and reconnect, launching flares of X-ray emission that can brighten the galactic center by factors of hundreds within minutes. These direct images represent humanity's first glimpse of the actual boundaries where space-time breaks down, but they reveal only the tip of an observational iceberg that has revolutionized our understanding of cosmic violence. The Laser Interferometer Gravitational Wave Observatory, LIGO, and its European counterpart Virgo have opened an entirely new window into black hole physics by detecting the ripples in space-time itself created when these monsters collide and merge. The first detection, announced on February 11, 2016, captured the final moments of two black holes spiraling toward each other at ever-increasing velocities before merging in a cataclysm that briefly generated more power than all the stars in the observable universe combined. The gravitational waves from this collision, designated GW 150914, traveled for 1.3 billion years across expanding spacetime before reaching Earth, carrying with them information about black hole masses, spins, and the fundamental nature of gravity operating under the most extreme conditions possible. LIGO's exquisite sensitivity allows it to detect length changes smaller than 0.000th the width of a proton, making it sensitive enough to measure the gravitational influence of distant cosmic catastrophes on the very atoms of its detector arms. The characteristic chirp of gravitational waves from merging black holes creates a sound that physicists have dubbed the song of spacetime, a rising pitch that accelerates dramatically as the black holes spiral closer together before terminating abruptly when they merge into a single, larger monster. The November 2023 detection of GW 231123 shattered previous records with the merger of two black holes containing approximately 100 and 140 solar masses, creating a final monster weighing roughly 225 solar masses. Both original black holes were spinning at near maximum rates, a discovery that challenges stellar evolution models predicting such massive objects shouldn't exist through conventional star formation processes. The detection revealed intermediate-mass black holes that were previously more theoretical than observational, filling a crucial gap in our understanding of how these cosmic monsters grow and evolve. Over 300 black hole mergers have now been detected across multiple observing runs, revealing a universe far more violent and dynamic than astronomers had previously imagined. The merger rate indicates that black hole collisions occur roughly once every few minutes somewhere in the observable universe, creating a constant background symphony of gravitational waves that carry information about cosmic evolution across billions of years of spacetime. These detections have revealed black hole populations that exist across an enormous range of masses and spins, from stellar mass monsters containing just a few solar masses to intermediate mass giants approaching 1,000 solar masses. The observed merger rates suggest that binary black hole systems are surprisingly common, indicating that the universe contains far more of these gravitational monsters than previous surveys had detected through electromagnetic observations alone. Recent discoveries have pushed the boundaries of black hole astronomy into realms that challenge theoretical understanding. MIT's discovery of V404 Cygnus as the first confirmed black hole triple system reveals a 9-solar mass black hole orbited by 2 stellar companions in a complex gravitational dance that suggests some black holes form through direct collapse rather than explosive supernova death. This finding challenges conventional models of stellar evolution and black hole formation, indicating that the universe creates these monsters through pathways more diverse than previously imagined. The James Webb Space Telescope has revolutionized our understanding of supermassive black hole formation by detecting these monsters in galaxies existing just 430 million years after the Big Bang, far earlier than theoretical models predict such massive objects could grow. These ancient supermassive black holes, some containing hundreds of millions of solar masses, challenge our understanding of how matter accumulates in the early universe and suggest that black hole formation might involve exotic processes operating under primordial conditions. JWST's discovery of little red dots, a new class of early galaxies hosting active supermassive black holes, reveals objects accreting matter at rates up to 40 times the theoretical Eddington limit, where radiation pressure should prevent further mass accumulation. These super-Eddington accretion rates indicate that early supermassive black holes operated under physical conditions that differ dramatically from those observed in the local universe, possibly involving primordial gas compositions or gravitational environments that no longer exist. X-ray observations continue revealing the detailed physics of matter falling into black holes through techniques that push observational astronomy to its limits. Iron K-alpha emission lines at 6.4 keV become dramatically broadened and shifted by strong gravitational effects near event horizons, enabling precise measurements of black hole spin through relativistic reflection spectroscopy. These observations reveal that many black holes rotate at 80 to 90% of their theoretical maximum rates, speeds that dramatically affect the structure of spacetime around them and influence the efficiency of energy extraction from infalling matter. The innermost stable circular orbit varies from 6 gravitational radii for non-rotating black holes to just 1.23 radii for maximally spinning objects, creating observable signatures in thermal emission and spectral line profiles that provide direct measurements of spacetime geometry near event horizons. These observations confirm general relativity's predictions with precision approaching 1%, demonstrating that Einstein's century-old theory accurately describes gravity even under the most extreme conditions in the universe. Ground-based observations have revealed the detailed structure of relativistic jets launched from supermassive black holes, creating particle accelerators that extend for millions of light-years while maintaining collimated beams with opening angles of just a few degrees. These jets transport energy and matter across intergalactic distances, influencing star formation in entire galaxy clusters and redistributing the heavy elements necessary for planet formation across cosmic scales. The discovery of gravitational lensing by black holes has enabled observations of matter orbiting just outside event horizons, revealing the complex interplay between gravity, magnetism, and relativistic fluid dynamics that governs accretion physics. Some observations show matter orbiting black holes at speeds exceeding 30% of light velocity, creating time dilation effects that are directly observable through periodic modulations in X-ray emission. Recent surveys have identified over 300 new intermediate-mass black holes in dwarf galaxies, plus 2,500 active black holes that were previously hidden by dust and gas. The closest intermediate-mass black hole to Earth, a 20,000 solar mass monster in the globular cluster Omega Centauri, sits just 17,000 light-years away, close enough for detailed study with future space telescopes. Yet for all these observational triumphs, the universe continues guarding its deepest black hole secrets with absolute fidelity. No observation has ever detected information escaping from inside an event horizon, confirmed the existence of singularities, or revealed what happens to matter and energy after they cross the point of no return. The theoretical possibilities of wormholes, white holes, and quantum escape mechanisms remain unobserved speculations that may never be testable through direct observation. The Event Horizon Telescope images show us the shadows of black holes but not their interiors. Gravitational wave detections reveal the final moments before merger but fall silent once new event horizons form. X-ray observations trace matter to the very edge of the point of no return but cannot penetrate the cosmic censorship that hides whatever lies beyond. Modern astronomy has achieved the extraordinary feat of making the invisible visible, but the most fundamental questions about black holes remain as mysterious as ever. We can photograph their boundaries, hear their collisions, and measure their masses, but we cannot observe their interiors, test their theoretical escape mechanisms, or determine the ultimate fate of information that crosses their event horizons. The real black holes that we've finally learned to observe confirm the mathematical predictions of general relativity with stunning precision, while simultaneously reminding us that the universe's deepest secrets remain forever hidden behind boundaries that no observation can cross. We have become witnesses to cosmic violence on scales that dwarf human imagination, but the witnesses themselves can never testify about what lies beyond the point of no return. In our quest to understand these gravitational monsters, we have achieved the remarkable feat of observing the unobservable, only to discover that the truly unobservable remains tantalizingly beyond our reach, protected by the universe's most perfect secret-keeping mechanism, the event horizon itself. Future revelations. What we'll learn next. Yet even as we celebrate these unprecedented glimpses into the abyss, the universe prepares to unveil secrets so profound that our current observations will seem like shadows cast by candlelight compared to the blazing revelations that await. The next decades promise to shatter the remaining barriers between humanity and the cosmic monsters that guard the deepest mysteries of existence, armed with technologies so advanced they read like science fiction and theoretical frameworks so revolutionary they challenge our fundamental understanding of reality itself. We stand on the precipice of discoveries that will transform black holes from observed phenomena into understood physics, potentially revealing whether the theoretical escape routes from cosmic doom represent mathematical fantasies or genuine pathways to liberation from gravitational imprisonment. The most ambitious leap into black hole astronomy's future comes from space itself, where the Laser Interferometer Space Antenna, LISA, prepares to revolutionize gravitational wave detection with sensitivity that will dwarf even LIGO's extraordinary achievements. Scheduled for launch in the 2030s, LISA will deploy 3 spacecraft in a triangular formation spanning 2.5 million kilometers, a detector so vast that Earth's entire orbit could fit comfortably within its baseline. Free from terrestrial vibrations and atmospheric disturbances, LISA will detect gravitational waves in the 0.1 MHz to 0.1 Hz frequency range, opening entirely new windows into cosmic violence that ground-based detectors cannot access. This space-based observatory will witness phenomena that exist nowhere else in gravitational wave astronomy. The years-long death spirals of massive black holes as they approach merger, extreme mass ratio in spirals where stellar mass objects spend thousands of orbits spiraling into supermassive monsters, and potentially even the gravitational wave background from the universe's first black holes formed in the primordial cosmos just minutes after the Big Bang. LISA's exquisite sensitivity will detect every supermassive black hole merger in the observable universe, creating a comprehensive census of cosmic violence that spans the entire history of structure formation. The prospect of observing extreme mass ratio in spirals offers unprecedented opportunities to test general relativity in its most extreme regime. When a stellar mass black hole spirals into a supermassive giant over thousands of orbits, it effectively becomes a probe mapping the space-time geometry around the larger monster with precision that no other technique can achieve. These observations will test Einstein's equations in gravitational fields billions of times stronger than those accessible to solar system experiments, potentially revealing deviations that could point toward new physics beyond general relativity. Ground-based gravitational wave astronomy prepares for its own revolution through third-generation detectors that will push sensitivity to theoretical quantum limits. The Cosmic Explorer, planned for construction in the 2030s, will feature 40-kilometer arms that extend LIGO's reach by a factor of 10, detecting black hole mergers throughout the entire observable universe and revealing the complete demographics of these cosmic monsters across all of cosmic history. The European Einstein Telescope, designed as a triangular underground facility with 10-kilometer arms, will achieve similar sensitivity while reducing noise through innovative isolation techniques that approach the fundamental limits imposed by quantum mechanics. These next-generation detectors will observe phenomena that challenge our understanding of black hole formation and evolution. They will detect the mergers of primordial black holes formed in the universe's first-second, intermediate mass black holes that fill the mysterious gap between stellar and supermassive varieties, and potentially even exotic objects like boson stars or gravastars that could masquerade as black holes while possessing radically different internal physics. The merger rates observed by these facilities will reveal whether our universe contains black hole populations that formed through exotic mechanisms unknown to current astrophysics. The Event Horizon Telescope prepares for transformations that will convert static photographs into dynamic movies of matter falling into cosmic monsters. The addition of space-based telescopes to the global array will extend baselines beyond Earth's diameter, achieving angular resolution approaching the theoretical limits set by the wavelength of light itself. These improvements will enable the creation of movies, showing matter spiraling into black holes over periods of hours or days, revealing the complex magneto-hydrodynamic processes that govern accretion physics in real time. Future EHT observations will target multiple black holes simultaneously, creating a comprehensive survey of supermassive monsters across the local universe. The addition of millimeter-wave telescopes in orbit will eliminate atmospheric distortions that currently limit image quality, potentially revealing fine structure within accretion disks and jets that remains invisible to current observations. These enhanced capabilities might detect the rotation of spacetime itself through frame-dragging effects that twist the geometry around spinning black holes, providing direct visual evidence for one of general relativity's most exotic predictions. Perhaps most revolutionary of all, the telescope arrays of the 2030s will attempt direct observations of black hole photon rings, thin circular features created by light that has orbited the black hole multiple times before escaping. These photon rings encode information about spacetime geometry with precision that could reveal deviations from general relativity or confirm the existence of exotic physics near event horizons. The detection and measurement of photon ring substructure represents one of the most challenging observations ever attempted, requiring technological capabilities that push astronomical instrumentation to its absolute limits. The James Webb Space Telescope continues revolutionizing our understanding of supermassive black hole formation through observations that peer deeper into cosmic history than ever before achieved. Future JWST programs will search for the universe's first black holes, potentially detecting objects that formed just 100 million years after the Big Bang, when the cosmos was still filled with primordial hydrogen and helium. These ancient monsters might reveal formation mechanisms that operated under conditions so different from the modern universe that they represent entirely new categories of astrophysical phenomena. JWST's unprecedented infrared sensitivity enables detection of heavily obscured black holes that remain invisible to optical and X-ray telescopes, potentially revealing hidden populations that could dominate the cosmic black hole census. The telescope's spectroscopic capabilities will measure the detailed chemistry of gas falling into ancient supermassive black holes, revealing how the first generation of stars influenced black hole growth in the primordial universe and how black holes themselves affected the formation of the first galaxies. The Nancy Grace Roman Space Telescope, launching later this decade, will revolutionize the search for primordial black holes through gravitational microlensing surveys that could detect these exotic objects across an enormous range of masses. Roman's wide-field imaging capabilities will monitor hundreds of millions of stars simultaneously, searching for the temporary brightening that occurs when primordial black holes pass in front of background stars. These observations could finally determine whether primordial black holes constitute the dark matter that makes up 85% of the universe's mass, solving one of cosmology's greatest mysteries. Roman's microlensing surveys will probe primordial black hole masses from fractions of Earth's mass to thousands of solar masses, covering the entire range where these exotic objects might exist in significant numbers. The detection of substantial primordial black hole populations would revolutionize our understanding of the early universe, revealing density fluctuations so extreme that they challenge current models of cosmic inflation and structure formation. Quantum computing applications to black hole physics represent perhaps the most revolutionary development in theoretical understanding since the discovery of Hawking radiation. Current quantum computers have already reproduced page curves and demonstrated holographic wormholes in simplified models, but future quantum systems with thousands or millions of qubits will simulate black hole physics with unprecedented fidelity. These quantum simulations will test fundamental aspects of the information paradox, explore exotic escape mechanisms, and potentially reveal new physics emerging from the intersection of quantum mechanics and gravity. IBM's quantum computers are developing increasingly sophisticated simulations of holographic systems that model the emergence of spacetime from quantum entanglement. These calculations demonstrate how gravitational physics can emerge from underlying quantum mechanical processes, potentially revealing that black holes represent natural quantum computers processing information through gravitational dynamics. Future quantum simulations might determine whether information falling into black holes is permanently destroyed or preserved through mechanisms so subtle that they operate below the threshold of classical physics. Google's quantum computer demonstrated the first artificial holographic wormhole in 2022, but future quantum systems will simulate increasingly realistic models of black hole interiors and wormhole physics. These simulations could determine whether traversable wormholes can exist in realistic spacetimes or whether they remain mathematical curiosities with no physical relevance. The quantum simulation of black hole evaporation might reveal whether Hawking radiation carries scrambled information about infalling matter or whether the information paradox requires entirely new physics beyond current theoretical frameworks. Artificial intelligence applications to black hole physics promise breakthroughs that could revolutionize theoretical understanding within decades. Machine learning algorithms trained on gravitational wave data are already discovering merger events that human analysts miss, but future AI systems will extract physics from observations with superhuman precision. Neural networks might identify subtle correlations in Hawking radiation that carry information about black hole interiors, or discover patterns in gravitational wave signals that reveal exotic physics operating near event horizons. AI analysis of Event Horizon Telescope data could reveal fine structure in black hole images that remains invisible to conventional techniques, potentially detecting signatures of quantum gravity effects or exotic matter near event horizons. Machine learning algorithms might identify systematic deviations from general relativity in gravitational wave observations, pointing toward new physics that operates under the most extreme gravitational conditions. The convergence of multiple observational approaches, gravitational waves, direct imaging, X-ray spectroscopy, and multi-messenger astronomy creates unprecedented opportunities for comprehensive black hole studies that will dwarf current understanding. Real-time alerts from gravitational wave detectors will enable rapid electromagnetic follow-up observations of black hole mergers, while improved Event Horizon Telescope capabilities will provide temporal movies of black hole dynamics synchronized with gravitational wave detections. Future multi-messenger observations might detect the electromagnetic signatures of matter falling into black holes during merger events, revealing how gravitational violence affects the material environment around these cosmic monsters. The combination of gravitational wave timing with optical observations could provide direct measurements of black hole spin evolution during merger processes, testing general relativity's predictions for how spacetime geometry changes during the most violent events in the universe. The most profound revelations await in the realm of quantum gravity, where theoretical developments suggest we may be approaching genuine breakthroughs in understanding the fundamental nature of spacetime itself. The apparent resolution of the information paradox through holographic methods, combined with experimental evidence from quantum computers and gravitational wave detections, indicates that black holes serve as natural laboratories for testing our most fundamental theories of quantum mechanics and gravity. String theory developments predict that future observations might detect signatures of extra dimensions or exotic matter states that exist only near black holes, while loop quantum gravity calculations suggest that quantum geometric effects might prevent classical singularities from forming. These theoretical frameworks make specific predictions about black hole physics that future observations could test, potentially revealing whether our universe operates according to principles more exotic than even general relativity describes. The next decade promises discoveries that will either confirm black holes as the ultimate cosmic prisons predicted by classical physics or reveal them as gateways to realms beyond current imagination. We stand at the threshold of answering questions that have haunted physics for nearly a century. Do singularities actually exist? Can information escape from black holes? Are wormholes real physical objects or mathematical fantasies? The universe prepares to unveil its deepest secrets through technologies that will transform theoretical speculation into observed reality, potentially revealing that the cosmic monsters we've learned to photograph and detect represent just the visible surface of phenomena so profound they challenge our fundamental understanding of existence itself. The future promises revelations that will either vindicate our current understanding or shatter it completely, replacing familiar physics with discoveries so extraordinary they dwarf even the theoretical possibilities we've dared to imagine. The next chapter in black hole astronomy will be written not in equations but in observations that push the boundaries of the possible into realms we cannot yet comprehend. The universe's greatest secrets await revelation through instruments that exist today only in blueprints and dreams, but which will soon transform the invisible into the inevitable, the theoretical into the observed, and the impossible into the undeniable truth about the cosmic monsters that guard the deepest mysteries of space and time. The ultimate question: would you even know you're doomed? But as we stand on the precipice of these revolutionary discoveries, one question towers above all others like a cosmic monument to human curiosity. In those final moments of your impossible journey, as space-time warps beyond recognition and the universe reshapes itself around your falling form, would you even realize that you're witnessing the end of everything you've ever known? This isn't merely a technical inquiry about consciousness and neural function under extreme gravitational stress. It's perhaps the most profound question about the nature of awareness itself, challenging everything we think we understand about the relationship between mind and cosmos. The answer reveals whether your journey into a black hole represents humanity's ultimate scientific experiment, or simply the universe's most elaborate method of ensuring that its deepest secrets die with those brave or unfortunate enough to discover them. The neuroscience of extreme gravitational environments remains largely theoretical, but the implications paint a picture both fascinating and terrifying. Your brain, evolved over millions of years to function under Earth's gentle 1g acceleration, suddenly finds itself operating in gravitational fields that can exceed Earth's pull by factors of millions or billions. The delicate electrochemical processes that generate consciousness, sodium and potassium ions flowing across neural membranes at precisely controlled rates, face disruption from tidal forces that treat brain tissue no differently than any other form of matter subject to differential gravitational acceleration. For stellar mass black holes, the question becomes academic before it can be answered. The violent spaghettification that tears your body apart long before you reach the event horizon would disrupt neural function within the first seconds of the process, as differential blood pressure between your head and feet exceeds the limits of cardiovascular function. Your brain requires a steady supply of oxygenated blood delivered at precisely maintained pressures. When tidal forces stretch your circulatory system beyond its elastic limits, consciousness would fade not from gravitational damage to neurons directly, but from the more mundane process of cerebral hypoxia, the same mechanism that causes fainting during high-G maneuvers in aircraft. But supermassive black holes offer a dramatically different scenario, one where consciousness might persist far longer than seems possible given the extraordinary nature of your situation. The gentle tidal forces at the event horizon of Sagittarius A* would allow normal brain function to continue unimpeded as you cross the point of no return, creating the surreal possibility that you might spend precious seconds or even minutes fully aware of your passage into the cosmic realm from which no information can ever escape. During these moments of continued consciousness, your brain would face the impossible task of processing sensory input unlike anything in terrestrial experience. The visual cortex, designed to interpret reflected sunlight from familiar objects, would struggle to decode the heavily redshifted and gravitationally lensed photons reaching your eyes from the warped spacetime around the black hole. The auditory processing centers would find nothing to interpret in the perfect vacuum of space, while your vestibular system, the inner ear structures that maintain balance and spatial orientation, would provide confusing signals as the very concepts of up and down lose meaning in the curved geometry near the event horizon. Yet perhaps most remarkably, the frontal cortex regions responsible for abstract reasoning and scientific understanding might continue functioning normally, allowing you to consciously recognize the extraordinary physics unfolding around you. You could potentially spend your final moments achieving insights into the nature of spacetime, gravity, and quantum mechanics that represent the culmination of human scientific inquiry. Discoveries so profound they would revolutionize our understanding of reality itself, if only they could somehow be communicated back to the universe you're leaving behind. The temporal aspects of consciousness during black hole infall create paradoxes that challenge our fundamental understanding of subjective experience. Due to gravitational time dilation, your final minutes of awareness correspond to hours, days, or potentially years of time in the outside universe. From your perspective, you experience a normal flow of consciousness, thoughts forming and dissolving at the usual pace, memories surfacing with typical emotional resonance, plans and fears cycling through your mind with familiar rhythms. But the universe outside undergoes dramatic acceleration from your gravitational reference frame. Stars that normally evolve over millions of years complete their entire life cycles during your final moments of observation. Galaxies collide and merge in cosmic ballet performances compressed into minutes of subjective experience. The entire future history of the cosmos might unfold before your eyes as you approach the central singularity, making you witness to the ultimate fate of everything that exists while simultaneously ensuring that your knowledge of these cosmic end times can never benefit the civilizations still struggling to understand their place in the universe. This creates one of the most poignant aspects of the black hole journey: the complete isolation of discovery. Every insight you achieve, every revelation about the nature of reality, every answer to questions that have puzzled humanity for millennia becomes trapped with you behind the event horizon. You become the universe's most knowledgeable observer at the precise moment when that knowledge becomes cosmically irrelevant, carrying ultimate understanding into a realm where understanding itself loses all meaning. The psychological impact of this realization, if your mind remains clear enough to grasp it, represents perhaps the most cruel aspect of the black hole experience. The human psyche evolved to share discoveries, to communicate insights, to build upon the knowledge of previous generations in an endless chain of intellectual progress. Finding yourself in possession of ultimate scientific truth while simultaneously cut off from all possibility of sharing that truth creates a form of existential torture that transcends physical suffering. Yet there might be strange comfort in the cosmic significance of your journey. Modern theoretical physics suggests that your fall into the black hole contributes to the universe's fundamental information processing in ways that operate beyond human understanding. If the holographic principle is correct, every thought you think, every observation you make, every quantum state that defines your neural activity becomes encoded on the black hole's event horizon surface, preserved in a form that maintains the universe's information content while appearing to destroy it from classical perspectives. This holographic preservation means that your consciousness might persist in ways that transcend biological death, existing as patterns of information encoded in the quantum geometry of spacetime itself. The universe's most advanced civilizations, operating with technologies billions of years more sophisticated than current human capabilities, might eventually develop methods to decode this information and reconstruct not just your physical form but your actual conscious experience during the journey into the black hole. The question of whether you would know you're doomed depends critically on your definition of knowing. If knowledge requires the ability to act upon information, then you would know your fate only in the most academic sense, aware of the inevitable outcome but powerless to influence it. If knowledge means simply understanding your situation, then your final moments might represent the most profound learning experience possible, as the universe reveals its deepest secrets to someone who can never share them. Recent developments in consciousness research suggest that awareness itself might be more fundamental than previously imagined. If consciousness emerges from quantum mechanical processes, as proposed by some theories of quantum consciousness, then your subjective experience might interact directly with the quantum gravity effects that govern black hole physics. Your awareness could become entangled with the exotic quantum states that exist near the singularity, creating forms of conscious experience that have no analog in normal spacetime. The integrated information theory of consciousness proposes that awareness emerges from the integration of information across complex networks. Inside a black hole, where spacetime geometry creates connections between distant regions through quantum entanglement and gravitational effects, your consciousness might expand beyond the boundaries of your individual neural network to encompass information processing occurring throughout the black hole's interior. You might achieve a form of cosmic consciousness that transcends individual identity while simultaneously approaching the moment of your destruction. But perhaps the most remarkable possibility is that you might not recognize your doom as doom at all. If the theoretical escape mechanisms proposed by quantum gravity turn out to be real, if wormholes provide passage to distant regions of spacetime, if black holes transform into white holes through quantum geometric effects, if the information paradox is resolved through mechanisms that preserve consciousness along with quantum information, then your journey into apparent annihilation might actually represent transcendence to states of existence that make current human consciousness seem limited. By comparison, the universe guards this ultimate secret with the same absolute fidelity that protects all information behind event horizons. No external observer can ever verify whether consciousness persists during black hole infall, whether awareness expands or contracts under extreme gravitational conditions, or whether the experience involves revelation or simply extinction. The cosmic censorship that prevents information from escaping black holes also ensures that the most profound questions about consciousness and reality remain forever unanswered. Yet, in contemplating these possibilities, we confront the deepest mysteries about the nature of existence itself. The question of whether you would know you're doomed when falling into a black hole becomes a question about whether consciousness represents a fundamental feature of the universe or merely an emergent property of complex matter arrangements. If awareness is fundamental, then your journey might reveal consciousness operating under conditions so extreme that they transcend current understanding. If consciousness is merely emergent, then your experience might simply fade as the material substrate of your brain succumbs to impossible gravitational forces. The cosmic irony remains that the most significant experiment in consciousness research would yield results that no one could ever analyze. You would become both the ultimate experimental subject and the ultimate secret keeper, carrying discoveries about the nature of awareness into a realm where discovery itself becomes meaningless. Your final moments might answer every question about consciousness, identity, and the relationship between mind and cosmos, while ensuring that these answers remain forever hidden behind the universe's most perfect information barrier. In the end, the ultimate question reveals itself as the ultimate paradox. Whether you would know you're doomed depends on mysteries so profound that they challenge our understanding of knowledge, consciousness, and existence itself. The black hole journey represents humanity's most extreme thought experiment, one where the experimenter becomes the experiment and the observer becomes the observed, crossing boundaries that separate the knowable from the unknowable in the most literal sense possible. The universe offers you the possibility of ultimate understanding at the price of ultimate isolation, cosmic consciousness at the cost of cosmic irrelevance, and absolute knowledge purchased with absolute silence. Whether you would recognize your doom might depend less on the physics of black holes and more on the nature of consciousness itself, a mystery so deep that even the universe's most extreme environments might not be sufficient to resolve it. The question echoes across the cosmos, unanswered and perhaps unanswerable, a reminder that some truths are so profound they can only be discovered by those who can never share them. Your journey into the black hole becomes the universe's most perfect secret, known only to you and hidden forever behind the cosmic veil that separates reality from whatever lies beyond the point of no return. In contemplating your fall into cosmic doom, we confront the ultimate limits of human knowledge and the final boundaries of scientific inquiry. The black hole awaits, patient and eternal, ready to reveal its secrets to anyone brave enough to cross the threshold from which no revelation can ever return. The answer to whether you would know you're doomed lies forever beyond the event horizon, trapped with you in the realm where questions and answers become indistinguishable from the silence of infinite space-time curvature.